Right, welcome to the RQI Circuit 2026. So this week we're here in Dublin. Local organizer is Joshua Jones. So the idea here is that this is a series of local conferences that have been taking place every week at a different RQI hub. RQI stands for Relativistic Quantum Information. It's an effort of the International Society for Relativistic Quantum Information. If you're interested in this community, in this society, and things like this, feel free to scan this QR code. This will take you directly to the registration page, and you can register there. We have no fees or nothing like this. But if you want to become a part of this community, we organize conferences regularly, yearly at the very least. And without further ado, then, please, Josh, if you want to invite the speakers here and say some words, feel free.
Yeah, so our first speaker is going to be Yasaman Yazdi, who is going to be talking about and career development at DIAS.
Thank you, and hello everyone, and welcome to DIAS. So the purpose of this talk is to give you a broad idea of the kinds of things happening here at DIAS and what it's like to work here, and also what some of the research work and other opportunities are here. Oops. So I'll start with a little bit of history of DIAS. So DIAS was founded in 1940, so it just turned 86 years old. It is the second institute for advanced studies and the first in Europe. It was founded by the famous statesman Eamon de Valera, who you can see in both of these pictures. So over here and over here. So this picture is from one of the first council meetings of DIAS in 1940. It took place in a government building. And this picture is from a conference here in 1942, and it features some well-known physicists, for example, Walton, Dirac, Eddington, and Schrödinger. So DIAS is a dedicated research institute, and it is comprised of three schools: the School of Theoretical Physics, the School of Celtic Studies, and the School of Cosmic Physics, which is composed of two sections, the geophysics section and the section of astronomy and astrophysics. This is a picture of the Dunsink Observatory, where some of our colleagues from astronomy and astrophysics are based. And the relativistic quantum information related research takes place in the School of Theoretical Physics, which we are based in right now. So DIAS has a very rich and unique history of supporting and valuing fundamental research. You will find a piece of that history in the folders that Josh prepared for you. It's something that I like very much about here. I work on the causal set theory approach to quantum gravity, which is very much a fundamental physics topic. You're going to hear more about it and other areas of research later today, so rather than tell you more about some of the current research at DIAS, I'm going to tell you a bit about the past research, or rather some of the past researchers that spent time here. So there's a visitor book that DIAS has that looks like this. And it was in use since the early days of DIAS. So I'm going to show you a few pages from this visitor book that will show you some of the people that spent time here visiting and working over the past 86 years. And you can also see what their handwriting looked like. So this is the first page from 1942. We have de Valera, Eddington, so I've just underlined some names that you'll recognize. Dirac and Walton. You can see their handwritings too. This is from 1943, Max Born, Schrödinger, and this is just a snippet from another page from the late 60s, early 70s. John Bell, Vaidya, Takahashi. 1972, John Wheeler. He also had a remark. The universe is far stranger and far simpler than we realize. Siyama, Casimir, Shield. Oops. Zeman, Higgs, Werner Israel, and Atiyah. Roy Kerr, who clearly didn't have good writing. Someone had to clarify that. Raphael Sorkin, Bela Ku. So this top part was from the mid-80s, and this from the mid-90s. Freeman Dyson, Etuf, 2000s, mid-90s up here. Oops. Now let's come back to current times. So these are a couple of group pictures, recent group pictures of the members of the School of Theoretical Physics. It gives you an accurate idea of the number of people here in the School of Theoretical Physics and the demographic distribution. So currently there are 2 senior professors over here, including Denjoe, who is the current director of the School of Theoretical Physics, here and here. 3 adjunct professors, I think one of them in the photo. 1 visiting professor, here. 4 senior postdocs, so here, and here, and here, here. 4 junior postdocs, here, 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 and I guess 4th one's not here. And 4 PhD students, here. Oh yeah, Marek. 4 PhD students, here, 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 and here. So DIAS is not a degree granting institution. So all of our PhD students are registered at another university. The current students are registered at Irish universities, but in principle, they could be registered at any university globally. And you can find a complete directory of all the people and their contact information on DIAS's website. I'll come back to the topic of the positions here at DIAS, but before doing that, I'll also mention that DIAS has a summer internship program which runs over 2 months, usually June and July. And this program is intended for students completing their 3rd year at an Irish university in line for a first-class honors grade and with an interest in a research career in theoretical physics or mathematics. So these students over the 2 months work on a project or sometimes 2 projects under the supervision of a researcher at DIAS, or sometimes more than 1 researcher. And so here's a picture from the cohort last year, and we currently have this year's cohort with us. Maybe those of you in the audience can raise your hands. Yeah. And there is also the possibility for final year honors or capstone projects to be carried out under the supervision of a DIAS researcher where the institution allows for that. So here is a list of the summer intern projects and and mentors for this year. It just gives you a broader idea of the research going on right now beyond what you will hear about later. So I'll just read some of the titles. Gravitational thermodynamics and boundary conditions, the adiabatic theorem in quantum mechanics, dark energy from causal sets, non-local green functions in causal sets, Bailey pairs, partition identities and quivers, SimPossible, crafting alternate universes, matrix models for membranes, robustness of quantum antibody scars to local impurities, regularization and anomalies in simple quantum mechanical systems. So there are three of the kinds of positions offered at DIAS are senior professorships, DIAS research fellowships, which are meant for more experienced researchers, typically with at least one postdoc position already behind them. These are 5-year positions. We have DIAS postdoctoral scholarships, which are meant for more junior researchers, typically with less than 2 years of postdoctoral experience after their PhD. And so the senior positions are for 5 years and the junior positions are for 2 to 3 years. And you can find any vacancies for these positions on DIAS's website in the vacancies section. So as you can see, there are no vacancies at the moment, but if there are any, they will be posted there. The national funding agency of Ireland is called Research Ireland, and you can find a list of opportunities and awards that they offer on their website. So DIAS can serve as a host institution for these awards and grants. And you should check the website regularly to see what things are offered, because the grants and awards are not necessarily regularly offered, so one has to check back to see which calls are open. And I think you can also sign up to be informed of any calls that you're interested in opening for applications. So some of the ones that are regularly offered, I've listed here. So one of them is the Pathway Program, which is a 4-year grant for a senior postdoc, and it provides funding for the postdoc, a PhD student, and various other research expenses. There is the Royal Society Research Ireland University Research Fellowships, which is another senior postdoc position, this one for 8 years. There is the EPSRC Research Ireland joint funding, which is a grant not for one's own salary, but for a research project and to recruit postdocs to carry out that research project. And it's in partnership between an Irish institution and an institution based in the UK. And the duration is for up to 5 years. And a number of international opportunities that can be held here are the ERC grants, the Marie Curie fellowships, and NSERC grants. So NSERC is a Canadian funding agency, and they have some fellowships that can be held internationally. And basically, anytime there is an opportunity where one has flexibility to hold that award or position, either anywhere internationally or anywhere in Europe, DIAS is an option to hold that fellowship or position or grant or award at. Switching topics a little bit. So we have weekly seminars on Thursdays at 2:30 p.m. The seminars are sometimes virtual, sometimes the speaker is here in person, and either way, everyone is welcome to join the seminars, either virtually or in person. The announcement for the seminars is shared through both our internal mailing list and the Irish Mathematics Distribution List, MathDep. So if you want to receive those announcements, you can either ask to be added to our internal mailing list, or you can sign up to this mailing list and you will also receive more general announcements of activities happening related to mathematics and theoretical physics in Ireland. If you would like to deliver a seminar, you can also contact a researcher that is relevant to your field. And we're happy to accommodate that in most cases, either online or in person again. Our seminars are recorded and put on YouTube for later reviewing. DIAS has a YouTube channel. And there are also more general opportunities to visit DIAS for collaboration or for taking part in the activities of the Institute. So some researchers here have their personal grants that they can use to support some of these visits. And the school also has a budget to support seminar speakers and visitors on some occasions. So reach out to us if you're interested in giving a seminar or visiting. And here's a list of some of the seminars that took place in the past year. So I'll just read some of the titles. The Non-Commutative Geometry of the Standard Quantum Sphere. Olivier Ricci Curvature in Non-Smooth Lorentzian Geometry and Causal Set Theory. Unification of conformal and fuzzy gravities with internal interactions. An Intro to Quantum Computing. The Big Bang as a Mirror. Universally Robust Quantum Control. Exploring Asymptotically Safe Quantum Gravity on the Lattice. DIAS also annually hosts a research forum which is meant for the postdocs and students within the different schools of the Institute to share their research to one another through discussions and posters. So this is just a picture from one of them. This is the poster from the last one that we had in October. DIAS also hosts outreach activities such as public talks. A particularly popular one is the Samhain August Science Festival, which is a series of Halloween-themed talks that take place around Halloween. And there's usually a talk from each of DIAS's schools, and it is marking the ancient feast of Samhain. So these talks aim to make the big scientific questions as well as Celtic history accessible and fun to a broader audience. Here are 4 of the talks that we had in the last edition of the festival. We had 2 from the School of Theoretical Physics, these 2. So one was Ghosts, Phantoms, and Monsters in the Battle of the Big Bang by Nyayesh F. Shorty and Phil Halper. And one was The Demons in the Details by Felix Flicker. These talks are also recorded and put on our YouTube channel, and even though they are meant for the public and a broad audience, they're also very fun for physicists. So if you haven't seen the talks, I really highly recommend that you watch some of them. They're enjoyable. Next, I'm going to say a few comments about some aspects of DIAS that are not directly scientific, but that have a lot of impact on how well we do our work. The support staff are very helpful, friendly, and attentive. And this includes the IT staff, the finance staff, and the central administration. The school administrator is George Rogers, and he's great, and he replies to emails very fast. There is a dedicated theoretical physics library with a very nice collection of books. There are great computing resources, including computer clusters. There are regular social activities that are organized, including movie nights, game nights, and tea time. Here are a few of the neighboring universities to DIAS. So there's Trinity, which is roughly a 25-minute walk away. There's UCD, which is roughly a 20-minute bus ride away. DCU, roughly a 45-minute bus ride away, and Maynooth, which is roughly a 75-minute bus ride away. So there are other institutions in the area that are easily accessible. And finally, because I know some people will be watching online from other countries, I just want to say that Dublin is a very nice city to live in. It is a little expensive, but it overall has ample arts and culture and museums and nature and friendly people. So a couple of my favorite places are the Museum of Archaeology, where you can find Celtic treasures and bogmen, and the Chester Beatty Museum, where you can find intricately illustrated books from the Far and Middle East. And DIAS itself is also located in a very nice neighborhood with lots of restaurants and cafes. So I hope this gave you a good idea of what it's like to be at DIAS, and that you will consider to apply for opportunities and positions to come visit here, work here, or take part in the activities of DIAS. Thank you.
Well, I guess, does anyone have any questions? Okay.
So you mentioned that you have no current vacancies, right? Do you have any forecast for when you might open some positions for postdocs or for senior postdocs or things like this?
I don't, but the person behind you may.
Hopefully later this year for the next cycle.
Thank you.
Any other questions? All right, well, let's thank Yasaman again.
Stick it on there somewhere.
Yeah, just wherever.
No, you stick it on there. That's fine. That'll be just where you think is close enough. Bless you. Go ahead. Right. Now, you have to do this funny stuff. We have to do HTML.
Yeah.
That's okay. Okay, that's it, right. And then this is going to work even though I stand here, and then Rick said I'll be in camera view, and then will this work? It will, yeah. Okay, great. Yeah, right. Okay, so I can start now, can I? Right. Thanks very much. I'm by far the oldest person in the room. In fact, I was trying to manufacture a joke based on how many people in the room's age would be bigger than mine, but it doesn't work, so I can't do that. Yasaman was showing you a picture which, if you're not familiar with the museum, you might not notice there was in the top right, there was a kind of blackish person. He's called the bogman, right? But I'm from Limerick, which is the southwest, which is a small city, although it's the third city. People who come to this big city, which is Dublin, are often rather disdainful of people who come from these small places. And one of the phrases they used to use, apart from culture, was bogman. So I'm really a bogman, but I can walk. Anyway, so this talk will just be about work, not that I'm doing some work on something to do with the flag manifold, the standard model, but I decided it would be much better to talk about this because I think it's more important than anything I can say. And it's really about work of Witten and collaborators on this sort of stuff. And people aren't always familiar with von Neumann algebras and entropy in the de Sitter space, so this will be quite elementary. It's not as if I'm an expert in anything anyway. Certainly my wife doesn't think I am. So let's have a look at a few little historical points. So these are kind of self-explanatory. 1865, people started talking about entropy not decreasing. Jumping to 20th century, well, Hawking, black hole areas, and then black holes emit radiation and particles, and then they looked at de Sitter space, and then very important breakthrough in this area is holography, as you know, and then a nice paper of Jacobson in 1995 was that if you have gravity and entropy, and you look at a few small extra assumptions, then you'll get Einstein's equation of state, which of course is a significant thing. Okay, now the other thing is that I don't usually have half an hour for a talk, I usually have more, but I try not to break the constraints of time. So let's have a few points, especially some people in the audience may not know all this. I don't quite know what their background is. So for a black hole, we have these parameters, horizon. This is a Schwarzschild black hole. And then Bekenstein said, well, BH stands for black hole there. The entropy of a black hole should be a multiple of the area. And that's what he came up with. And I have this thing now that I never use, but it's quite good fun. There's a stick here, but you can't rely on that. It might not exist. So we have this here. Now, what about that? Well, that's not quite the final story because, so here is what this number looks like. If you put Boltzmann's constant equal to 1, you get this capital C, which is 0.002. And then Hawking had his famous a quarter. So Hawking said, well, actually, I have a way of calculating which says that this number is not 0.0275, but is 0.25. So that's a rather nice thing and attracted a lot of attention, quite justifiably so. And then we have the fact that there's thermodynamics. This is really amazing because, you know, when I was a graduate student, which is a long time ago, early 70s, gravity and thermodynamics did not seem to be related. They were different subjects. But now Hawking says, well, okay, a black hole can have a temperature, T8 for Hawking, and if that's the case, thermodynamics comes in. And then a black hole emits things very faintly, and the lifetime, so it gets smaller, is looking like this. It's proportional to a multiple of the mass cube, and that multiple is a small number, which you see there. Okay, so I'm just reviewing. Oh, yeah, right. But this is like off stage. I've never been an actor, so, you know, off stage there. So now we have to move on to de Sitter space, which is basically what our universe looks like. And let's say a few things about de Sitter space to remind people. De Sitter space has got constant positive curvature. So that really means that not the Riemann tensor, but the Ricci scalar is all you need. And the Einstein tensors are like this, and this object becomes just that, proportional to that. So the field equations are there. And then there's a solution for empty space where there's no matter if you have lambda equal to a quarter of the Ricci tensor. This is all very well known, but very important. So now I want to get on to a few details which I'll need for the subsequent discussion. There's a thing called a static patch that one can talk about in de Sitter space, right? And it's the region that is causally accessible to some observer. And then I'd like to consider how one defines the event horizon cosmologically for an observer. So remember, the event horizon is something that came into physics when black holes were talked about. There's an event horizon, but now this is an event horizon associated with de Sitter space. And we would say that it's the boundary of the past of the observer's world line. Or if you like, it's equivalent to also saying that it's the boundary of the region from which light can never reach the observer. So the English grammar there is a bit annoying. You have to think from which. But anyway, if you sit down in a corner and nobody talks to you, you can understand it. And then, because we've now got two horizons, I've written that this is the horizon for the black hole, BH is black hole, and this is the other one for de Sitter space, just so try and minimize the confusion. And then you can also say, as this equivalently, this is also the boundary of a region from which light can't reach the observer. Now, the thing that's different about this red one, the one from de Sitter space, is it depends on the observer. It's not unique. So it will be different if you have a different observer. However, one thing about it which is useful is the area of the observer's event horizon is unique. Right? So it's different, but it has the same area. That's for de Sitter space. If you took a more complicated space than de Sitter space, that would not be true. This bit about the area would be wrong. It would change. But the contrast one wants to make before moving on is that if you have a black hole, you just have an event horizon. There's only one of them, and it's unique, trivially unique. So that's a little thing to bear in mind. So in 1977, just looking at the time, Gibbons and Hawking said to themselves, well, let's say they wrote a paper, which said that this de Sitter horizon is formally similar to a black hole event horizon, and it obeys similar area increasing laws. So that's very interesting. And associated to this de Sitter horizon should be a thermal radiation, just like it is associated for black holes. So that paper looks into this, and they say, well, get a very similar formula, almost identical. The de Sitter entropy is like the black hole entropy. It's a quarter of the relevant area, which in this case is the de Sitter area of that. And then because de Sitter space is such a simple space, it's practically flat, but not quite. It's amazing that our universe seems to accommodate it experimentally. There's a relation between the cosmological constant and this. So it's just 12 pi over lambda. There's all numerics are very simple. But that's what seems to be the case. So in other words, if I put one there, the de Sitter entropy is 3 pi over the cosmological constant. But then Bekenstein, a very clever guy, he said, well, I'm going to consider what I call generalized black hole entropy, because I'm going to include not the entropy of the black hole by itself, but I'm also going to have the entropy of things outside. So you can see it there. I've written S black hole, which is a quarter of the event horizon area, plus that. And then Bekenstein said, well, you can have this assertion now that this generalized entropy can never decrease. Okay, so that's an assertion, and it seems to be right. And with various assumptions, you can even prove it. But anyway, never mind exactly the logical structure of it. That's what the claim is. I think that's important for what I'll say later with the phenomenal algebras is that the black hole entropy has no upper bound. It can be bigger and bigger and bigger. It's just a quarter of this area, so it's bigger and bigger and bigger. So it's not got an upper bound. And that's also true for this guy. But the generalized, but now if I jump to the paper that I really want to talk about, these results of Witten, which were, I put 2022 here, but if you look at, that's the archive. The latest archive version of this I looked yesterday is 2023, and it's published already, so 2022 or 2023, but the archive will take you there. So this Witten et al., where et al. Means Chandrasekhar, Longo, and Pennington, they wrote a paper, and they suggested there's a generalized de Sitter entropy. Right? So it's exactly like this. They're copying this. So it's this plus this. And they say it never decreases. So the important thing is it never decreases. So if it's a sum of things, then we have an interesting thing here because, you see, it's a pity it won't fit on the slide, but you can't have everything. This generalized guy has an upper bound. It's a Polytom number. So it's a sum of these two, S out. So if one goes up, the other has to go down, and vice versa. So that's an important thing to remember. It's different from the black hole entropy, which is, not bounded. So it has a finite range, as I put in here. So now we want to get to the kind of quantum mechanical way of discussing entropy, which is to think of degrees of freedom as being provided by the quantum fields that we believe to be there. So we believe, at least, in the morning we do, in the evening we might be worried about it, that this static patch is filled with quantum fields. Okay. And the finite entropy means that if we want to describe entropy with degrees of freedom, the number of degrees of freedom in this patch will be some number. So it won't be infinity. So that's called n. And the entropy is rather easy to see. It will be given by some multiple of n. Multiple will be actually easy to see in a particular calculation. So that means that if the quantum fields are there, they belong to a Hilbert space. One's familiar these days with Hilbert spaces always being used for finite dimensional vector spaces, but they used to be just used for ordinary infinite dimensional vector spaces. So the Hilbert space of this static patch, right, in de Sitter space is finite dimensional. So what is its dimension? Well, this is a familiar thing to undergraduates. You take some quantum system whose Hilbert space is a vector space, which we call V. But if you've got a whole load of independent systems, you tensor them. There's n factors here. So the dimension of this is this to the power n. And the log of this, which is the usual useful thing in entropy, is therefore proportional to n. So I said the entropy is going to be proportional to n. So you suspect that the entropy will come in there. So entropy, I said, was equal to a multiple of n, where the multiple is called c. So this turns out this c is the log of the dimension of that space. Okay. And if we ignore the dim v just for convenience, so it's not strictly right, then the dimension of this e to the n, which is e to the s, which is this, right? So you have this thing. So let's be not theoretical physicists, but practical physicists for a moment, because what is this number? I mean, my wife might ask me, but of course she won't remember when I told her, and she'll probably tell me that she doesn't believe me. But this number, it's 3.8, this, right? So if you divide by log 10 to the base e, you'll get the number of decimal digits here, which is quite big, right? But when you've looked at that for a while, I kind of say, well, why couldn't it be 10 to the third 54 or 55? And you know, I begin to disbelieve the physics. Whoops. Okay, so a static patch is probably, if you believe this, some kind of very, very large dimensional vector space. Now, what have we got, mathematically speaking? Well, we're now shifting to a more mathematical discussion. Von Neumann entropy is an entropy where you look at a thing called a density matrix, which I hope you're all familiar with, and it applies if the space that we're dealing with, in our case it's this guy V, is finite dimensional. And what you do is you take this density matrix, which is called rho, and you take the trace, it's a finite number because this is a finite dimensional vector space, and you put a minus sign there, and then you compute this. So what would that be in linear algebraic terms? Well, this is a density matrix, and there's a spectral decomposition. So these are spectral projections. So this pi I just projects here onto the eigenspace of the eigenvalue lambda I. These lambda i's are in the interval 0, 1, and because there's a probability involved, they have to add up to 1, so they can't be anything. So if I do that, I get this thing here. And what you see is that, you see, they add up to 1, and they belong to this interval. So it's rather easy to work out that this, because the log of something less than 1 is negative, that means that unless you put a minus sign here, that would be a negative number. So this is positive only with that minus sign there. I draw attention to that because it comes up in discussion of Witten et al.'s work, okay? And then there's some technical terms which get used in this language, not too many of them. If this is a projection, so this is a sum of projections, but there might only be one projection, right? That'd be a very simple case. And then because of this, that would just be the identity, right? And that's called a pure state, and it's also called a projection of rank 1. But if that were the case, if there were only one eigenvalue, and it was equal to 1, you'd have the log of 1 there, so this would be 0. And the entropy would have to be 0. So for this so-called pure state that the mathematicians like, the entropy has its lowest value. So it goes from 0, if you remember, to 3 pi over lambda, so that's minimized. Okay, and there's a little objection that I like to put in here, which is just a C Nash objection from the Bogman. I hate that term, pure state, because it all comes from this guy, Irving Siegel, not to be confused with Graham Siegel, who was a very clever guy, and he introduced I think he used the word C-star algebra for the first time in print. At least I wasn't able to see one earlier than that. And he talked about states. And he meant by states positive linear functionals, which is pretty fancy. But it's very easy to get a positive linear functional related to this density matrix. You just take the trace of rho acting on a vector, and that's a number, and that's a positive linear functional. So that's the way that works. But I wish he hadn't used the word state, because when I was a tiny boy in quantum mechanics class, I looked at the Schrödinger equation and it had states, and he reused it. And it would be nice if he could have thought of something else. So that's my objection. Anyway, if we get the minimum for 0, where do we get the maximum? Well, actually, if they're all equal, then we get the maximum, which is this. So that's when all the lambda i's are equal. So basically, you can see what that is. If rho is equal to a multiple of the identity, the multiple has to be 1 over the dimension of v, and then this all fixed together. And so this is called a minimized. SVN is minimized, this is maximized. And this is called a pure state, and this should have the word impure in it, but it doesn't. It's called a maximally mixed state, and the terminology gets a bit irritating. But anyway, it's terminology, so don't worry about it too much. Okay, so that's a little bit of finite dimension linear algebra a la von Neumann, because you can do quite a lot with this. It's not a trivial approach at all. So then, for what we want to talk about in the end, we have to know what entanglement is. So, and that's a very big topic these days. There was a seminar about it yesterday, which I didn't go to because I wanted to think about this talk. But sorry, I would like to have gone, because it mentioned entanglement. So it's a property of tensor products. You have to remind students of this. It's not a property of a space by itself. So you want to see whether the A guys can be mixed up with the B guys, and maybe more of them. Okay. This is all elementary enough. And it can be quite well discussed if you use a density matrix. So that's why I say that. So it's enough to get an intuition of this. It's enough to look at just 2 entangled things. You can obviously have many more, but you can get the main ideas by understanding what happens here. So if we've got this situation, then the possibilities for a density matrix is 1 for this, and 1 for the whole thing. So we have them there, right? So that's fine. So what will we learn from entanglement and density matrices here? Well, we, first of all, have 2 definitions. If you have the density matrix of the whole thing, let's look at the second line first. If the density matrix of the whole thing is a sum of the tensor product of the density matrices with some positive coefficients here, they can't be negative if you think about it, then that's called separable. Really, what happens in this B space and this A space they don't really communicate much with one another. But that might not be true. And so if it's not equal to it, we have a name for that. So this is entangled, and this is separable. And it's not entangled and non-entangled, or separable and non-separable. They have to have 2 words. So if you want to discuss entanglement, you can use what are called Bell states after John Bell, because actually 2 dimensions is enough to give you something non-trivial. But you would have to have at least 2 dimensions, as I put here. So it's amazing that really all the intuition you need, practically, will come from understanding these Bell states, which are only small 2-dimensional Hilbert spaces. So let's have a little bit of notation. D1/2, that comes from the representation theory of the Lorentz group. Sometimes they use D1/2. So we have a spin-1/2 particle, and we represent it on the 2-dimensional representation. And let's say that both these spaces are the same. There's the copies of one another. So we've got one copy of this 2-dimensional, another copy. And these are called by a fancy name, which you've all heard of, qubits. It took me a while to understand that they had used an unnecessary new name, because new names are not good, in my view. You should use old ones. So let's take a basis of each space, and this is meant to indicate whether the spin is up or the spin is down. So for one space at a time, you can only have spin up or spin down, and so on. So an orthonormal basis for the tensor product would have to be 4-dimensional. So these are plus, minus, parallel, and anti-parallel. And we just have a look here. I won't write them all out. So E plus means there's a plus sign here. E minus would mean there was a minus sign there. And then parallel means that spin is pointing in the same direction. So that's a parallel one. And that's pointing in the same direction as that. So that's also parallel. So there are 3 similar expressions you can make. There are 2 more parallel ones and 2 anti-parallel ones. So this is all fine. And these are called Bell states after John Bell. And this basis is these vectors here. They're all what you would call entangled vectors. So let's see what that means. So we can have a density matrix for each possibility. So try and do it there. So rho plus or minus this is equal to this with a plus or minus there, and that's the dual of that space there. You know, you can represent a matrix by a tensor product of a space with its dual. That's the equivalent way of writing a matrix, and it's the obvious way to do it here. And then the antiparallel ones, you just have AP here. So we've got our 4 density matrices, and it's very convenient to use this formula for the Bell states. But you can easily check, and it's just an assertion here, that these all are pure states, so they have entropy 0. And we can also check that they're entangled. So I haven't done that. I'm just claiming that now because I can't do everything for you. But it's very simple. You write them out. In fact, it just follows. If you look at the previous transparency, you can see they're entangled. And if you can't see that, then just put on another pair of glasses. So the interesting thing is that mixed states and entropy can partially characterize entanglement. So if you're looking at entanglement, you should maybe have a look at that sentence. So here's a characterization of maximal entanglement. Oh, let's speed up a bit. Supposing you have a matrix for the HA tensor HB, then you might take the trace of not all of it, but just the B part of it. And it's called a reduced density matrix, then it's called rho A. You could also do it the other way. You could take trace of, you could put an A here and rho AB here, and you'd call that rho B. So this seems to be democratic between the two guys. So you might wonder, is this rho A guy and this rho B guy the same in this case? Well, it is the same. Not in every case, but in these cases, rho A and rho B will be the same. So you're not losing anything by just discussing this rho A. And the rho B guy, this is really driven mathematically by its eigenvalues. And the rho B, if I wrote a B here, would have the same eigenvalues. That's why it's going to be not containing any different information. So what is the entropy of this reduced one? And so this trace means you just trace over, if you like indices, which I don't, you just contract over the indices belonging to the vector space A. So here's an observation which is not totally obvious, but it is fit on one page if you try to calculate it. If this guy was pure, then this would have 0 entropy. Any pure state always has 0 entropy. And it also means somehow that although it's pure, this partial density matrix here is mixed. And as soon as this is mixed, it has non-zero entropy. Pure means it has 0 entropy. And if you're not pure, you have to have some entropy. Now, here's the thing that I think they had fun thinking of these names. Purification, it's nothing to do with religion or hygienics in health terms. It's a purification of a mixed state. So you've got a mixed state here, and then you can make a bigger density matrix of the kind I had here. And you can write this out, and it turns out that if this is mixed, there's always a pure rho AB. But it has to be on a larger space, clearly. It's not unique, though, because if you gave me one of these things, I could say, oh, I'll just take a bigger vector space with trivial entries, and it would still be a pure state. So when this is maximally mixed, to me, this is a multiple of the identity matrix without a 1 here, with us 1 over some positive integer, then we call that maximal mixed. And what the connection between entanglement and entropy is that if this is maximally mixed, we get this. So it's maximally entangled. In fact, that's often used as a definition of the term, maximally entangled. It's like this. So now we go to the von Neumann entropy. It's maximized, let us say, so then it has to be log n. And supposing A and B are entangled, then this number is a kind of measure of that entanglement. So this is a bit more non-trivial than what I said before. So you maybe just should accept it. The entropy of this, the number here, this guy here, is a measure, a precise measure. So this guy can go from 0 to log n, but this guy's here with the AB is a single number fixed at 0. And these Bell states that there were 4 of them. They're all maximally entangled according to this definition and any other definition. Now, okay, I have to go a little bit faster, but this is always a trouble. So von Neumann algebras, they were invented by Murray and von Neumann. Poor Murray never gets a mention after that, I don't know why. So let's take a look at the whole slide at once. Hilbert space, but now it's typically infinite dimensional. Not all the time, but most of the time. So when it's infinite dimensional, you wonder whether you've got bounded operators. So this means the bounded operators. And then an algebra, which is a vector space with a product, is called a von Neumann algebra if it has an identity in it, if it has a star operation, and if it's closed with respect to the inner product. So finite dimensional examples exist. So this means K by K matrices, they're trivially a von Neumann algebra. And then infinite dimensional examples. Well, that's the main one, because actually all von Neumann algebras that you encounter in the definition, well, all of them, by definition, they all sit inside here somewhere. But the reason I put this finite and infinite is there's an in-between type of example called a hyperfinite von Neumann algebra. And it is infinite, but it's almost finite. It's actually approximation can be constructed by approximation of finite dimensional algebras. And that's a very important property because there's only one way of doing that. So, as I say, approximated by sequence of those. Then there are C-star algebras. So von Neumann algebras are a special type of C-star algebra. Every von Neumann algebra is a C-star algebra, but not the other way around. So let's say here, if you take the compact operators, then that's a C-star algebra, but it's not von Neumann, because the identity operator is not compact. Okay, because it has an infinite range. Okay, so that's just a little bit of technical remarks about the difference. In topological terms, a C-star algebra is closed with respect to the norm, and von Neumann algebra is closed with respect to the inner product, and one is a stronger condition than the other, so that's why you have this nesting of the two. Then, technical term, if the von Neumann algebra has a center, and it's trivial, or it's a multiple of the identity, it's called a factor. And then we use an element notation P to describe projections. So a projection is something that's equal to P squared, and also in this case, it's equal to its adjoint. And just recall, because this is important here, that if you have a projection, the trace is the dimension of this target space here, right? And V might not be equal to W. Then you can have two projections which might be equivalent if you have this situation. If P is equal to U star and Q is equal to U star U, remember the star has gone away, then you say that these are equivalent. So if these were the same space, they could be equal to one another, but they're not. And then there are three kinds of von Neumann algebras, usually called 1, 2, and 3. And there are many equivalent definitions of what they mean, these things mean. But the most important thing is, for us, is that this is the cleverness of the von Neumann algebra, is that there's a new phenomenon about dimensions. So let me just look at this for a moment. Take all the projections of some von Neumann algebra and call it capital P of A. And then take this map, which I haven't told you how to define yet. There's a map called D, and D is meant to remind you of the word dimension, because that's what it really contains. There's a map from P to the positives, and it also includes infinity. So this map can take the value infinity. And if two projections are equivalent, like this partial isometry thing I wrote down, then it turns out these dimensions are the same. If they project onto different spaces, then you see this additive thing is here. And if P is what's called a finite projection, I haven't time to tell you what that is, it says that this is finite. So this really should be thought of as a trace, because these are properties of a trace. Now here comes the interesting thing, is that let us take RD, R stands for range, the range of this dimension map. And we have to normalize it, so we would say that the dimension of the identity is going to be 1 in our language. That it can have the following possible properties. If it has the values 1 to n, if this is what you discover, then you have a finite dimensional von Neumann algebra. You've got the n by n matrices. If you have an infinite dimensional matrix, right, then this n is allowed to be infinity. So these are two discrete possibilities. But then if you have this famous kind called a type 2-1, which is the one we need, then the dimension is no longer even discrete. It's a continuum, and it's bounded below and above. It's up to normalization 0, 1. That's the way they know it. And then there's type 2 infinity, which is what happens with black holes. And you have a continuum going right up to infinity. And then there's so-called type 3, which are discrete. So this is what I'm saying here. Is this really a trace-like map? And it is. And I say the answer is yes. But the remarkable fact is here, you think of these guys as giving you the dimension of a space, but the dimension of a space up to now was never anything except an integer. But now you're saying it can be in between 0 and 1, which is new and very important and very natural as well. So that's what I'm saying. There's a continuum of dimensions. And then we can also go up to infinity under the right conditions. And then I also had, the very last one was type 3, and there's only 2 possibilities. So this is not a square bracket, this is a chain bracket. You can only have 0 or infinity. So these are very weird guys, the type 3 guys. So von Neumann and Murray in their original paper show that there is a unique trace-like function. Now I'm going to call it tau to distinguish it from TR. So it's not the normal trace. If you took the normal trace, which is TR, you would find that the trace of the identity is infinity, but you wouldn't find it here. In fact, you'd find this tau of I is equal to 1. But it has these properties. And similar trace functions exist for all the von Neumann dimensions. We only want one of them. And we want this hyperfiniteness one. So this is what we want for our de Sitter, or Witten and company want for their de Sitter arguments. So I'll have to speed up a little bit. In 1964, Araki wrote a paper which was saying that free field theory has got a type 3 von Neumann factor associated with it. Well, that means that there's no well-defined entropy, because my previous slide showed you that you can only have the value 0 or infinity. 0 is trivial, infinity is a kind of pathology. So now, black hole entropy, de Sitter entropy, they fit in. Let's look at de Sitter entropy. So if you have a row belonging to, so these density matrices are now promoted to belonging to an algebra. If it's of type 2 infinity, then you can have this formula, and this is the same formula works for type 2, 1. So these are finite numbers. So they would bypass the divergence of as n goes to infinity, because you see these are infinite dimensional spaces and then these are finite numbers. So you haven't got an infinity. But there's a big problem with the sign, because you see, if you look at the tau of which I had to have on the other one, I won't bother going back to it. The tau thing is a genuine trace and it's positive. It's between 0 and 1. So if you have tau here, this is positive and then that goes negative. Right? It's not like the ordinary trace. So here you're in trouble. So you have to put this right with this entanglement argument. So here is a Bell qubit, if you like, but it's a pair of them. So take a lot of qubits, label them with A and B, and take n of them, and write this vector down. So this is vector space HNA and another vector space HNB. And if you tenth of those, you get another space HA. And look at the entanglement of that. And actually, the algebra works fine. Now you take capital of psi. Well, it's all written here. You can see exactly what these are. And it looks like this. And it belongs to this space here. And you can easily check it. You know, it fits on half a piece of paper. But that's maximally entangled. And the density matrix is this guy. And its partial trace is maximally mixed. And actually, that comes out in one line here. This will be maximally mixed if this is a multiple of the identity. And I haven't left anything out here. If you just stare at this, you realize this is just all you need. So that's very good. So the entropy is a maximum, and this is equal to this. But we have to relate the n goes to infinity to a type T1. So this is what happens. If you take the qubits and you disentangle some of them, say k of them, what will happen is the n log 2 will become n minus k log 2. And then if you keep on doing that, you're going to reduce this down by an infinite amount. And so that's what happens in the paper of Witten et al. They say, take n go to infinity, and we have this new space where you take this, and you are able to construct a renormalized entropy by this thing here. Now, that's all I can say here because there isn't space to go any more. So this I call the renormalized entropy, and it differs from this by an additive constant. So this, if I didn't renormalize it, the de Sitter space entropy would go from minus 3 pi over lambda to 0. But I wanted to go from 0 to 1. So there's an additive constant which you can stick in here and make it go from there to there. So I've written that here. So this fits in. So then the von Neumann algebra was an algebra of observables. And so this is the formal claim that you'll see in the paper. Kind of nice statement. The observables are really this guy here. And then the black hole entropy, you want to go from there to there. But you'll have a similar problem with the sign there. But there is a similar renormalization you can do to get that to work with the von Neumann case. You take a tensor product with what's called R. I haven't told you what R is yet. It's not the Ricci scalar anymore. And you can make the black hole entropy and the von Neumann entropy agree. So here is the von Neumann. Vn stands for von Neumann. Will do that. As I just said, there's a problem with this TR. But if you use the tau thing, you can put that right and make this go from 0 to infinity. I didn't write that in the slide there. So then I've really just got maybe one more slide, and that is that this R here, I shouldn't have used R maybe because although it's used in all the mathematics books, it's also the same as the Ricci scalar. But it stands for this hyperfinite factor. So there's only one of those. Now the way we've constructed our R, if it didn't pass you by, is we've taken a tensor product of n things and we've let n go to infinity. So it is an approximation of a series of finite dimensional spaces to an infinite dimensional space. But the thing that's true in von Neumann algebras is there is only one von Neumann algebra which is constructed that way. No matter what you do, you'll always get the same one. But it won't look the same usually because there's some isomorphism. So here's a very good thing that I think is relevant physically. You can also look at Clifford algebras, and the simplest Clifford algebra you can look at is this. And then you can take that tensor product of n Clifford algebras, and then you can take n going to infinity, and then you get a von Neumann algebra, which is easy to check. So you constructed this by a finite dimensional approximation. So is this the hyperfinite von Neumann type 2-1, which is meant to be unique? It is. So that's a rather nice thing, because physicists like these Clifford algebras, and there are things to do. There's a nice book by a man whose surname is Plyman, P-L-Y-M-E-N, Roger Plyman, which is called something like Spinners on Hilbert space. You can look at this. And another thing is, final remark, I thought this would be nice to throw in. If you have the anti-commutation relations, so not the commutation relations, but the anti ones, then you write this down in von Neumann algebra terms. And if you construct this for an infinite dimensional space by this usual finite dimensional approximation, you get a von Neumann algebra, and it's another instance of the hyperfinite R. So we've met R in three ways. We've met it by tensoring n qubits and letting n go to infinity. We've met it by canonical anti-commutation relations, and you can meet it by the Clifford algebra one, which I had it on the previous slide. So I think that's a good place to finish. Sorry, I had to go fast at the end, but that's... Oh yeah, so gravity saves the day. You see, Witten likes to make a lot about this, and I think he's definitely right. If you didn't have gravity, you wouldn't be able to save the entropy. You'd be in a type 3 situation where the only entropy was either naught or infinity. But if you allow gravity in, then you have de Sitter space, and de Sitter space's entropy can be renormalized in the way Witten explained, and you will have a proper account of the entropy. So, okay, thanks. I think it's coffee now, is it? Oh yeah, questions.
Yeah, so I think there's no time for questions, but there's a coffee break now.
I crashed the thing by 6 minutes, but
It'll be downstairs, and yeah, we'll come back here in 25 minutes. All right, thank you all for coming back, and some of you guys for showing up for the first time. Our next speaker is going to be Marek, who's going to be talking about semi-classical space-time thermodynamics.
Thanks a lot, Josh. So, hi everyone, I'm Marek Liška, I'm a postdoctoral scholar here at DIAS, and I'm going to tell you a little bit about how to get essentially gravitational dynamics from semi-classical reasoning and thermodynamic equilibrium arguments. I would like to credit Charles for borrowing me his stick. It is incredibly useful. And this is a work that I've chiefly done with my former thesis supervisor, Ana Alonso Serrano, and her student, Michal Piotrak, who is currently at UCL. I would also like to mention contributions by Luis Garay from Madrid and some other people, but this is the main gang for the project. And okay. The idea of the talk is to first tell you a little bit about the whole gravity from thermodynamics program, which I believe has some interest, and then as a sort of proof of concept, I'm going to move the whole discussion into two-dimensional JT gravity. And in particular, I first introduce the concept of generalized entropy in 2 dimensions, then show you how the semi-classical dynamics of JT gravity actually emerge from this generalized entropy, then briefly comment on what sort of problems we are going to face when we try to move to 4D, which is, of course, more natural dimension. And I'll end up with some future perspective that will tie things up with fancy words like von Neumann algebras and quantum reference frames, hopefully justifying why I'm talking about this at RQI Circuit. So first, the main idea of gravity from thermodynamics is actually fairly simple, dates back to an old paper by Ted Jacobson from 1995, and the idea is that, okay, you study gravitational dynamics applied to causal horizons, and this can be, as Charles said before me, black hole horizon, it can be de Sitter horizon, it can be cosmological horizon, but it can also crucially be observer-dependent horizons. It can be Rindle horizon, that is just horizon seen by accelerating observer, entirely observer-dependent, non-gravity behind it. Can be horizons of causal diamonds, which is just the maximum causal development of a space-like ball in your space-time. And in either case, the dynamics take a form analogous to the laws of thermodynamics. You have the second law saying your entropy, suitably defined as R over 4, does not decrease. You have first law relating this change of entropy to your change of energy. For black holes and some other cases, you will have third law preventing you from reaching 0 temperature state by finite number of operations. And on top of this, you can add quantum field theory in curved spacetime, as Hawking and Unruh originally did, introduce a physical notion of temperature associated with the horizon. So for black hole, it is the famous Hawking temperature going with the surface gravity. For acceleration horizon, it's going to be Unruh temperature directly proportional to the acceleration of the observer. And for de Sitter, it's going to be temperature scaling with inversely with square root of the cosmological constant. And in this way, you make the horizon genuine thermodynamic entities, at least in principle, moving from analogy to real correspondence. And one very crucial thing that is usually not so much stress is this, all right, does involve gravity, and gravity was the way to originally derive it, but a lot of the results, and essentially all the crucial results, namely the first and second law of thermodynamics, are essentially consequences of quantum field theory. Unruh effect, that is just statement about restricting your algebra of observables to some region about the presence of the horizon, otherwise it all follows from quantum field theory, not even in curved spacetime, in flat spacetime. Entanglement entropy, well, that's a feature of vacuum fluctuations on both sides of the horizons that are correlated, and of course this correlation, when you're missing one side, you get some entropy as a consequence of that. Rick was talking a lot about it yesterday at the seminar for those who were present. And for matter fields, we just can compute their standard von Neumann entropy, density operator times logarithm of density operator with a minus. Again, perfectly quantum field theoretical thing. And we can state an equilibrium condition between this entanglement entropy of vacuum fluctuations across the horizon and between von Neumann entropy of matter fields present inside the region. And crucially, this equilibrium condition, or first law, if you will, is equivalent to equations governing gravitational dynamics. Originally, this was shown in more classical way by Ted Jacobson in 1995, as I said, but then he improved upon himself in 2015 and showed this exactly in this way, presenting the Einstein equations as a condition on entanglement equilibrium of small causal diamonds. So the whole program actually works very nicely in 2D as long as you're dealing with Einstein equations. You can even talk about semi-classical Einstein equations in the sense that you can get expectation value over energy momentum tensor on the right hand side, but you cannot explicitly deal with back reaction of quantum fields on the space-time. That becomes very untractable in 4D. So our solution, suggested originally to us by Andy Svesko, who in the end did not join the project, but I would like to give him credit for the original idea, is going to 2 dimensions, where, of course, you don't have gravitational theory in the usual sense. Your Einstein tensor is trivial, there is no graviton, but you can add non-minimally coupled scalar field and talk about the dynamics of Jacques-Teitelbaum gravity. That is a thing that's been around since mid-80s and actually has some very nice mathematical feature that make it very useful toy model for many things. And in this case, we can essentially talk about generalized entropy rather explicitly. So to demystify it a bit, generalized entropy is really just the entropy of the horizon. In our case, understood as the entanglement entropy of the degrees of freedom across the horizon, and the von Neumann entropy of matter fields all summed together. So it is just equivalent of the total von Neumann entropy of the region of the spacetime. And in particular, there is a nice feature in 2D, the JT gravity, the generalized entropy of a black hole, even some dynamical black holes, corresponds precisely to Wald entropy of the black hole, giving us a very simple procedure for computing. To get Wald entropy, you essentially simply take Lagrangian of your theory, you differentiate with respect to Riemann tensor, and integrate the result over the horizon. Of course, in 2D, you don't have a horizon, you have a point, so you essentially just take the value of this derivative in the point. And this was shown by Pedraza, Svesko, Sibesma, and Manu Swisser already some 5 years ago. And they also showed that in the semi-classical 2D context, this generalized entropy has 3 contributions, or you can think of it conceptually as being 3 contributions. Of course, in the end, the power of the generalized entropy is that you sum them together and treat them as one thing. Leading order entanglement entropy of the horizon, which really is just the Wald entropy in the most usual sense. Then you have von Neumann entropy of quantum matter fields present there, which in the black hole case you usually don't deal with. And of course, here when I say matter fields, I implicitly mean minimally coupled. Non-minimal coupling adds its own problems, but we don't have to concern ourselves with that so much. And then you have corrections to the entanglement entropy of the horizon that comes around from back reaction of the quantum matter. And this is precisely the part that can be formally treated in JT gravity very well and becomes very cumbersome in 4D. And as I will try to convince you in the following, all these have purely kinematic origin. They are simply consequences of quantum field theory in curved spacetime. And we can then use them to derive gravitational dynamics without presenting a circular argument. So the argument I'm going to tell you crucially is not I have Wald entropy, which I got from Lagrangian of my field theory, and then from this Wald entropy I'm getting gravitational dynamics. That of course is rather circular because in the beginning was already your Lagrangian, which gives you equations of motion in much more straightforward way. I'm going to use that as an inspiration and maybe to some extent as a computational simplifying factor, but in fact everything is phrased entirely in terms of quantum field theory. So, first we have the leading order contribution to the entanglement entropy of the horizon. This is again just the entropy of the vacuum state of the quantum field. And in higher dimensions, the leading order contribution to this scales with the ARA. It is the famous ARA over 4 Planck length squared. So in particular, we can assign such entanglement entropy that really flows from vacuum fluctuations to the horizon of a higher dimensional extremal black hole. Imagine Reissner-Nordström black hole such that its charge is equal to its mass in natural units. And the horizon then admits effective two-dimensional descriptions in terms of JT gravity. And in this effective two-dimensional description, when you rewrite your entanglement entropy scaling with ARA, you will essentially get that this entanglement entropy becomes some constant, proportionality constant, times the value of the scalar field. This scalar field there appears not as something put by hand, but as a scaling factor of your metric that upon dimensional reduction, you can essentially treat as a scalar field. So in this way, this entropy proportional to a scalar field emerges from QFT in curved spacetime in 4D. You just make dimensional reduction, and then you make a leap of logic that, however, is essential for any gravity induced by thermodynamics program, which is, okay, I got this for a black hole horizon, but I wanted the same answer to be true for any causal horizon in my theory. And you can get from entanglement argument fairly easily that it will be true up to a renormalization constant eta. So I'm going to keep eta here undetermined for now and only determine it later on as a result of thermodynamic reasoning rather than as something predetermined. Next, pardon, going too far. We have the von Neumann entropy of the matter fields. There the situation is fairly simple. For simplicity, we should consider small variations of fields away from vacuum. In that way, we can still comfortably split the entanglement entropy from von Neumann entropy of these matter fluctuations. And in this case, the von Neumann entropy is given by modular Hamiltonian of your theory divided by Unruh temperature. That is fairly simple for conformally invariant quantum field theories. In that case, this Hamiltonian is a local operator that is just proportional to the expectation value of your stress energy tensor. For non-conformally invariant field theories, you can still essentially arrive at very similar, slightly deformed result when your theory has fixed ultraviolet Gaussian points. So essentially you have a point in UV where it behaves as conformal field theory and you can expand around it. If you don't have this, then there is essentially no nice local expression for the modular Hamiltonian and you have to do it the hard way. So for simplicity, I'm sticking to CFTs and then the entropy is simply this. It's the time component of the expectation value of the energy momentum tensor times time integrated over some piece of horizon because I'm actually computing change of entropy here. I'm interested in a physical process situation, so I'm computing the difference of entropies between two places that on the horizon that are connected by a surface sigma. Of course, in 2D, this sigma is just a line. And then this is just a factor coming from the Unruh temperature that stays there. And one thing I would like to point out, to compute this entropy locally for local causal horizons does require that you rely on Einstein equivalence principle in the sense that you need to be able to introduce local reference Minkowski vacuum and get Unruh effect with respect to that. Again, in 2D, you can probably go beyond that by appealing to your global anti-de Sitter vacuum being present there, because essentially the only possibility for 2D gravity is to have constant curvature, and usually you stick to negative cosmological constant for phenomenological reasons. So there you could go further, but in general, in high dimensions, equivalence principle really comes into this, and it's an important ingredient. Next, we go to the quantum back reaction, which is, in the case of 2D, fully captured by the conformal anomaly. That is non-local, but you can always describe it by effective local Polyakov action of this form. So you have an auxiliary scalar field chi, which is non-minimally coupled to curvature and has a kinetic term. That's all. And then you can compute the corresponding entanglement entropy fairly easily, for example, via replicatory calculation, and you will arrive at this term that scales with the field and the kinetic term of this form that essentially has similar structure to the stress energy tensor term I showed before. And once again, this is just quantum field theory in curved background. This time really in curved background because we have the scalar curvature entering.
What is alpha?
Oh, alpha is essentially just your measure of acceleration. It's not particularly important. So basically, the acceleration of my Unruh observer is 1 over alpha. That's the whole idea. And now let's put all these pieces together, finally. So we have 3 contributions to entropy. We imagine this as a piece of light cone, and normally you would have to deal with the fact that this evolution is not really so simple, and then you have some expansion of your light cone in flat space-time that changes the volume of it and has to be treated separately. But in 2D we have no such problem because this term just trivially vanishes. So we get fairly simple equilibrium condition that would just be the change of leading order entanglement entropy of the horizon plus the change of Polyakov part of the entropy, the quantum back reaction, plus the change of matter von Neumann entropy. I would like to say is 0, but that would be only true if you have no potential for the scalar field. When there is the potential of the scalar field, you get an extra term there, which we decided to interpret as the work being done by the scalar field, essentially by the exterior of the light cone on the light cone itself. So we put this potential there as an external force. Having external force as a gradient of the potential is essentially quite natural thing, although I have to admit we currently don't have microscopic explanation for why this should work that way. So for now there is some formal similarity with this looking like a work term plus the fact that it makes the equations work out. There definitely needs to be more set in the future. And when we do this, when we add this work term here, that is just the scalar field potential plus some extra term that we keep, we get this fairly simple condition coming directly from here, where this field T mu is just our arbitrary direction of the time that we chose in the beginning to construct our causal horizon. And since this choice was entirely arbitrary, we can make a different choice and reach the same equation, just there will be a different time-like field here. And when you think that through, it means that for this to be valid for any unit future-pointing time-like field here, it must be valid as a tensor identity for the thing inside the bracket. And from that, when we take the divergence of the resulting equations and set it to 0, we will eventually obtain 3 equations. One of them is this beautiful tensorial one. Then there is one relating the scalar field potential with curvature, and the third one is essentially D'Alembert equation for the field chi. And together, these three equations are equations of motion of semi-classical JT gravity, just with arbitrary potential. In normal JT gravity, this V would be phi over L squared, L being your measure of the cosmological constant, the associated length scale, and this would just tell you the scalar curvature is constant given by your cosmological constant parameter in the Lagrangian. Otherwise, these are fully the equations of JT gravity in the semi-classical case, just more general. And it is coupled to conformally invariant quantum matter, which again we could probably push further to the cases with Gaussian fixed point, but there is no real need to do that. So in 4D, things become a lot more complicated because there is an R squared term in the conformal anomaly, which cannot be recovered from any local action. So it cannot be forced by any usual fields. And nevertheless, okay, anyway, this comment means it cannot be sourced by the usual conformally invariant matter fields. It has to be sourced by some exotic matter. So perhaps we can simply throw it away, and then we obtain some sort of effective local equations of motion from thermodynamics as before. So in this case, the only problem is 4D conformal anomaly does not quite get you the correct asymptotics of Unruh vacuum in black hole spacetime, strongly suggesting that it's not the whole story on quantum back reaction. We need some extra components, and we have no idea how they could look. One option here would be to really embrace that the back reaction brings in some non-locality and treat this seriously as a non-local gravitational theory, but of course that is much more complicated. So just to end, let me comment on how to actually connect this with von Neumann algebras and with essentially relativistic quantum information formalism. So the first option, very clear, is to rephrase the derivation in terms of von Neumann algebras. In this case, we can use that the algebra associated with interior of the local causal horizons is type 2 infinity. We can compute entropy, we can do a lot of things. And this is going to be largely trivial, probably won't lead to any new insight. What I expect to lead to new insight is to apply quantum reference frame formalism. So essentially to introduce some quantum fields giving me my reference frame with respect to which I construct the causal horizon and let them back react. In this case, Michal Piotrak has recently showed that the dynamics that you get do not depend on the choice of the clock in two-dimensional theory. So the idea there is essentially you apply Page-Wooter's formalism, you construct your clock system, you let it interact there, and the result is not affected by any choice of the clock, which is fairly encouraging. Seems like we could obtain some genuinely diffeomorphism invariant results even in the quantum reference frames framework. But of course, this is limited to 2D, and it's limited to having just quantum reference clock, not the spatial measures that will require a lot more difficult math. But in 2D, it should be tractable. Then the question, of course, is the change of the frame relevant for the dynamics you get? And this goes crucially far beyond the semi-classical case and can give us some real insights into what the quantum situation might be. That's it, and thank you so much for your attention.
All right, does anyone have any questions? Right. Well, in that case, can you go back to your conclusion?
Yeah.
So this business of, well, actually, I have two questions, actually.
Okay.
But probably the first question should be about the JT gravity, right?
Yes.
As I understood it, you looked at like this entanglement.
Okay. This won't be a problem.
You looked at essentially like an equilibrium equation for,
Yes.
well, with work
Yeah.
for entanglement, and you get out dynamics of JT gravity.
Yes.
Is that surprising, or did you somehow put in the fact that it is JT gravity?
I did not. I would say JT gravity in 2D has similar status as GR in 4D in the sense that once you add in equivalence principle and the simplest entropy scaling you can think of, you will recover JT gravity.
But as in, so let's say you wanted to get out some other theory of two-dimensional gravity, right?
Then you have to put in by hand information about your world entropy, which is essentially equivalent to choosing your gravitational Lagrangian.
Okay.
So there is some
Okay, so
sense
it's
in
in
which
the world
JT
entropy
is
term.
chosen, but it's chosen as the simplest possibility. Nothing more, nothing less.
Okay. Yeah. And then I guess my other question is, well, do you know why? So generically, when you put in the clock as a quantum reference frame,
I
right?
see.
The entropy itself depends on the clock, right?
It does.
But so, is there a reason why it shakes out that the gravitational dynamics don't depend on it? Is it that?
It does seem that you will have some. What we did not consider, for instance, is the case of having two clocks in a superposition. We don't consider superpositions of space-time, so there is some. Maybe we are skipping in the original proof some cases where it can be an issue. And I would say ultimately the reason is that having 2D gravity and just these local causal horizons that have nice symmetries to them and are essentially in flat spacetime is so restrictive that, okay, the entropy depends on the clock, but it depends essentially in the same way no matter which clock you choose. Seems to be the case.
So do you think it's a two-dimensional thing, or do you think it's a generic
there
thing?
is, it looks like it may be two-dimensional thing.
Okay.
Probably in 4D. My gut feeling is that it will not work that way.
Okay. All right. Thank you.
Thanks.
Anyone else? Right. Well, let's thank Marek again.
Thanks, Alex.
There's also this thing. Yeah, if you just put that in your pocket, I guess.
Wait. So I want to share here, I guess. That will hopefully. Yeah. And let's see if we see
Click.
does that. Okay.
All right. Our next speaker will be Brien Nolan, who will be talking about classical and quantum instability in of Cauchy horizons in self-similar collapse.
Thanks, Joss. Thanks for the invitation. So as you can see from the first slide there, I'm based in DCU. I'm on sabbatical at the moment, and I guess that's something else that happens in DIAS. There's a sort of a support here for people who need to hide out from their universities when they're on sabbatical in case they're asked to do anything. So this is almost entirely going to be about classical general relativity. Perhaps unwisely, there'll be a little bit at the end about the quantum picture that applies here. I think it might be worth spending just 1 minute drawing a couple of pictures which are going to come up just to explain some background there. So I'll start off with a picture of the universe, and the universe has time and space, and it extends to infinity in all directions. That takes up too much room, so the first thing I'll do is I'll get rid of that and think of this as a radius. This is relativistic, so null cones are going to be important. So we travel at the speed of light. We might be traveling inwards, we might be traveling outwards. I put a coordinate, what do I want here? I want V going out in that direction, and I want a null coordinate U going out in that direction. It still takes up far too much space. So Penrose introduced this very nice idea of compactifying along the U and V directions, which mathematically in some sense is very, very simple. We just transform by taking an inverse tan of these coordinates U and V. And the upshot is that we get to draw the entire universe in a finite domain. And when we follow these prescriptions, we get this diamond structure or half diamond structure. So I still have R equals 0 here. This thing is called I plus, future null infinity. That's where you'll end up if you travel infinitely in the V direction. And you might have come from the infinite past in the I minus direction. Particles, matter, doesn't travel at the speed of light, travels less than the speed of light. And if we follow the rules, we find that matter particles will go from here up to here. We might have a whole bunch of matter, for example, a star. And a star will look like that. And if this star happens to collapse all the way down and form a black hole and a singularity, we get a picture like this, where somewhat mysteriously this is also R equals 0. Okay, so a picture like that is going to be important because there's going to be variations of that. So everything, we have the 45 degree angles for the null directions, singularities are wiggly lines. Okay, so meanwhile, this is what I'm going to talk about. So I'm going to talk about, Vijay space-time representing the gravitational collapse of pure radiation, maybe of a cloud of photons. I'm going to look at a case where this is self-similar so that length scales are replicated as time evolves. I'll talk about the connection between this model and the so-called cosmic censorship hypothesis of general relativity, which is really about the global evolution properties of the Einstein equations. This will lead me to be concerned about perturbations of this Vijay space-time model, which is spherically symmetric. I focus mainly on classical perturbations, and then, like I say, at the end, I'll say a few words about quantum fields. And we should probably stop the recording for that bit because I don't know if I want that to be out in public. Anyway, so Vijay space-time, we're in general relativity, so the key thing is the space-time metric. We also need to know what manifold we're working on. The manifold here is quite simple, nothing complicated. It's spherically symmetric, perhaps, is a key thing. My V coordinate, which is the same as the V coordinate I mentioned a moment ago, ranges over the whole real line, and we have a proper radius or that ranges over the half line. This looks very much like Schwarzschild, and indeed you can get this metric by just writing down the metric for a Schwarzschild black hole and taking the mass parameter to depend on this advanced V coordinate. But in fact, coming at it from another way, this is the unique spherically symmetric solution of the Einstein field equations of general relativity, where the energy momentum tensor represents null dust, traveling tangent to this null direction k, with the local energy density mu having this characteristic form. Okay, so we think of a thick shell of photons that are undergoing gravitational collapse. They just have energy density, they don't have any pressure, so the collapse is going to go all the way down to a singularity. Now look at this thick shell model where we have a hollow sphere, a hollow thick shell of photons, and in the middle there's no mass, and we have a theorem that says then that it must be flat space-time. Then we have some matter, and then outside the matter, well, there's a constant mass interior to it, so we'll have the Schwarzschild solution on the outside. So this gives us this picture. I went one too far, did I? Oh, jeez. So just to mention a few things about this model. It gives rise to naked singularities, and actually I do need to go to my picture then. Because what we see happening is when we follow the rules for drawing one of these diagrams, okay, we get a collapse down to this singularity that happens in the future, time, of course, is always moving up the page. But we also get this strange part of the singularity that, as you can see from the diagram here, I need Charles' stick here. As you can see from the diagram, once we're past this C plus region, we're into a domain where we can see this singularity in the past. So the singularity is called naked because it's visible. It's not hidden inside a black hole. And if you think that singularities are bad because they crush objects and so forth, and it's the end of the evolution of the space-time, naked singularities are really very terrible indeed. And I'll try and convince you why that is. So nothing travels faster than the speed of light. And gravity, in a very shorthand way of saying it with lots of footnotes, travels at the speed of light. And certainly doesn't travel any faster than the speed of light. So the gravitational signal travels at and less than the speed of light. So if I want to solve the Einstein equations using an initial value problem, and I mean, what better way to spend your life than trying to solve the Einstein equations? What would we do? We'd say, okay, well, here's what's happening at some instant of time, maybe a sigma t like this, and we'd solve a Cauchy initial value problem. We'd specify initial data, evolve the Einstein equations, and use that data to figure out what does the rest of the space-time look like. However, when we go up past this C plus region, we can't see the full initial data set, which we need to do to construct the solution. So up to C plus, that's fine. The Einstein equations will tell us uniquely what the space-time is. But once we're past this C plus, which is called a Cauchy horizon because it presents a horizon to the Cauchy initial value problem. Once we're past C plus, we can't see the full initial data set, and we don't have unique evolution in this region. So that sounds a bit like, well, why is that different from a singularity? Well, a singularity, you know, we run into this singularity inevitably in the future, but here we're in this region of space-time where there's no extreme curvature. You know, there's nothing strange with the curvature here. It's not blowing up. We're in a perfectly finite domain, but we have this fundamental problem with the Einstein equations. So this is really a statement about the mathematical nature of the Einstein equations, that they admit these solutions where, the evolution fundamentally cannot proceed because of the presence of this naked singularity and the associated Cauchy horizon. Okay, so what do you see if you see what you do if you see a Cauchy horizon or something like this? You hypothesize it away, and this is exactly what Penrose did in the late 1960s. He hypothesized that generically solutions of the Einstein equations should not give rise to this kind of configuration. And it doesn't take, well, actually, yeah, maybe I'll go on to my next picture. Yeah, so when we evolve initial data from some initial hypersurface sigma, and I'm using this compactified picture again, we maybe can evolve all the way out to infinity to the right and to the left. We might meet a singularity. That's, you know, it's inevitable in some circumstances, but we shouldn't be too fussed about it. But the really terrible thing is if we meet a Cauchy horizon, because then in this orange region, we don't get unique evolution. We don't know how to continue the space-time. So this is the cosmic censorship conjecture, that when we take generic, asymptotically flat, regular initial data, the maximal globally hyperbolic development, in other words, when we push the data as far as we possibly can, it should be inextendable. So we don't meet a regular surface like this Cauchy horizon where we can continue the geometry across. Singularities, typically we can't continue the geometry across. It's fundamentally broken at that stage. So we shouldn't see this. But if we do see that in an initial data set, what we should expect is that if we make a small perturbation of the initial data, whoops, no, that's not good. There, yeah. If we make a small perturbation of the initial data, that we would expect instead to see this picture, that rather than having a Cauchy horizon, we would get a singularity. So, another way of expressing the cosmic censorship conjecture is to say that Cauchy horizons should be unstable. And there's lots of results about this. There's lots of mathematical work on this, and work in the physics literature as well. This has kind of stopped cooperating for some reason. Sorry. Maybe if I do that. Whoa, no, this is totally just jammed. Okay. Okay, so that's my question then in relation to this Vijaya space-time. It admits a Cauchy horizon for a certain range of parameters. Is this horizon stable or unstable? So how do we tell if something is stable? Well, we solved the Einstein equations to produce this space-time. So with a certain set of initial data. So we'll perturb the initial data and see what happens when we get to the Cauchy horizon. So that's what the rest of the talk is about then, is looking at these perturbations. There's been previous work on this. So Waugh and Lake in the 80s were the first to address this problem. I'll come back to this idea that what we're looking for here is essentially some kind of blue shift instability, that radiation or indeed matter fields, their energy content, and if we think of energy in terms of a frequency, gets shifted into the blue, and we get runaway blue shift, indicating that there's some sort of blow up of energy density at this Cauchy horizon that leads to a singularity. So Waugh and Lake looked for this just in terms of light signals propagating up to the Cauchy horizon, didn't find it. Bonnier and Mallet looked at perturbations of this Vijaya model. They were more concerned with behavior at infinity. So I looked at this problem about 20 years ago with a PhD student, Thomas Waters, who's in Portsmouth now. So there were some things that I didn't know how to do at that time that I do know how to do now, and this is why I'm looking at it again. So what we did at that stage, we looked at individual modes of the perturbations. We did a spherical harmonic decomposition, then did a frequency decomposition. We started in 4 dimensions, we're down to 2 dimensions, so we're just looking at 1+1 evolution problems. So we weren't able to resum the modes properly, and also we didn't properly consider this boundary between the matter-filled region and the flat region inside, and I'll come back to that. A couple of more recent papers looked at quasi-normal modes in this space-time and drew various conclusions. This paper from a couple of years ago, Capuano et al. Calculated quasi-normal modes, which are extremely important in black hole perturbation theory. So huge swathes of certainly the physics literature on black hole perturbation theory is described using these quasi-normal mode tools. So these are basically sort of a basis for the set of perturbations. I'm kind of skeptical about this because quasi-normal modes in the black hole case, you're looking at solutions that are finite at the black hole horizon and out at infinity. The modes these guys look at are actually between 2 different horizons in the Vijaya model. So their conclusions about global perturbations are a little suspect to me. There's also some studies of conformal scattering by Coudray. So that involves looking at a signal that's propagating in from I- and scattering to I+. This is for not infalling radiation, but outgoing radiation. So really, as far as I can tell anyway, it's only this earlier work with Thomas Waters that addresses this stability problem. Okay, so there's a whole bunch of technical stuff that I'm not going to go into that yields the linearized Einstein equations. So the metric and matter perturbations can be decomposed in into what's called odd and even parity sectors. Okay, so the background that we're perturbing, this background metric is spherically symmetric. So there's naturally the spherical bit and the 2-dimensional T or time and radius sector. So that's I'd call that the Lorentzian sector, the 2D Lorentzian sector, and then there's the stuff on the sphere. So that immediately gives us a way of decomposing the perturbations. We can look at the TOR perturbations, the 2x2 bit there. We can look at the perturbations of the spherical sector, and then we can look at the cross term. So we immediately have that decomposition, and then we can apply further decompositions. So to produce this equation, well, it's a spherically symmetric background, So it's very natural, and a lot of the work employs a harmonic decomposition. So we decompose scalars into spherical harmonics, vector perturbations into vector harmonics, and tensor perturbations into tensor harmonics, all built up from the set of spherical harmonics. There's a nicer approach, well, I think it's a nicer approach that uses something called the Hodge decomposition. And if you Google Hodge decomposition, well, when I did, you get very complicated stuff about algebraic geometry, but there's a very simple consequence of the Hodge decomposition for one forms on the two sphere, which is really useful. It tells us that any covariant vector on the sphere decomposes into the gradient of a pair of scalars. So this allows us to decompose all of our perturbations, the scalars, the vectors and the tensors, into a set of scalars defined on the sphere, depending on T and R. And we turn the handle on all of this, and the odd parity sector we find reduces all the way down to a single wave equation for this master. So we have this master equation for this scalar phi that's completely determining the odd parity sector of the perturbations, and I'm not really going to say anything about the even parity. Okay, so now we have a very well-defined mathematical problem. So really now it becomes a problem in analysis. The geometry has sort of, in some sense, kind of faded into the background. We have a wave equation. This is the wave operator on the Lorentzian bit. There's a Laplacian from the sphere, and there's a perturbed energy density from the background null dust. So our task then is to, well, just see how initially regular perturbations, in other words, initial data for this PDE, how those data evolve as we let the perturbations move through the space-time and impinge on the Cauchy horizon.
Is this spherically symmetric?
The background is spherically symmetric. These are non-spherical perturbations.
Okay, so angular momentum, like you don't have a curve type?
No. But the perturbations induce angular momentum. Actually, there's a technical reason that I have to switch off dipole perturbations and deal with them separately. But this is L bigger than, so it includes all of the quadrupole and higher perturbations, and in particular includes the gravitational wave perturbations. Okay, so we need to think carefully about perturbations being initially regular. These perturbations, if you what's my next one? Yeah. So we have these perturbations. Remember, in the background, and this is the picture of the background, this region is flat space-time. So when we perturb that, we get nothing but gravitational waves. These gravitational waves will propagate across C minus, and it's flat space-time, so nothing peculiar is going to happen there. So we need to build into the initial data the fact that it's finite on C minus. Okay, so yeah, I won't show you the previous slide because it has just a bunch of equations on it. The picture, I think, tells us the important stuff. Okay, so I'm zooming into this sector of Vijaya space-time, and the geometry gives me very naturally, and the self-similarity, which I didn't really say very much about at all. So this, in the self-similar case, this mass function in Vijaya space-time is a linear function of the advanced time. It naturally provides us with this time coordinate just given by V over R. And as a time coordinate, then we get time slicing right throughout this region here. And this is the region that I'm interested in, bounded by the Minkowski region to the past and by the Cauchy horizon to the future, and plus and minus null infinity as well. Okay, so the game we play is to pose regular initial data on some sigma t0 and ask what happens when those data propagate to C+. Yeah. It isn't, no. It's a past, so it's the past horizon of this central point, the central singularity. Yeah. So we're posing data here, asking what happens to that data when it gets to C+, but then also asking, well, did that data come from something finite on C minus? Okay. So, okay, it's a 3+1 PDE, but it's linear. because we're just looking at the linear Einstein equations. So this doesn't sound too complicated. It sounds like it's hyperbolic, so I can look up my big book of hyperbolic PDEs and figure out how to solve it. What makes it a bit non-trivial is that this master equation is singular at C minus and at C plus. So it has something that's very much like a regular singular point in a second order linear ODE that everybody learns about as an undergraduate. But because it's a PDE, we're in 3+1 dimensions, it needs a little bit more work to deal with it. But there are standard methods available in the PDE literature for dealing with this kind of thing. And they're all based on, well, the approach I've used is to use these energy integral methods. Okay, so this is very standard hyperbolic PDE kind of arguments. We define some kind of energy norm. We check the way that energy norm evolves. In the very simplest case, for the wave equation on flat space-time, this energy is conserved. Okay? If the energy is conserved, well, then the field itself can't be doing anything strange. It can't be blowing up. We don't get conservation, but we do get control. We get bounds on this energy. The very first thing we write out and do is, well, you see a PDE, it's second order. Say, well, I'll write it in a first order form. Then there's a natural energy, which is just the norm of the first order reduction. This has the dimensions of energy. It looks like a sum of kinetic and potential energies. We ask how it behaves, and we find that this diverges as we get to the interesting points, reflecting the singular points in this equation. So we have to work a bit harder and build improved energy norms to control things as we move up to the horizons. So the basic idea is we take the standard energy, and that will work all the way up to this sigma T plus, and then we let the improved energy take over to bring us to C plus, and then we do that in the opposite direction. We devolve back to sigma T minus, and then use an improved energy to get all the way, to sigma T minus, and then we devolve back to C minus using the improved energy. And then we can have a theorem that says nothing goes wrong. I'll try and leave a little bit of time to say some stuff about the quantum things. So the theorem says there's no evidence of instability in the odd parity sector. We can pose, and these are, these kind of function spaces that are standard. These are the ones that represent the fact that we have initially finite energy. These are Sobolev norms. Little bits of technicality. We need to control a first derivative on the real line. We need to control two derivatives on the sphere for reasons of Sobolev embedding and stuff like that. But the basic idea is that we can control the energy all the way from C minus up to C plus. And so regular perturbations remain finite when we get to the Cauchy horizon. And you will notice that that's bad news, right? The idea was the Cauchy horizon is supposed to be unstable. That's not showing up for linear odd parity perturbations. So what else might go wrong? Well, the first thing to check at the classical level is to consider even parity perturbations. But in some other circumstances, in some other circumstances, for example, Cauchy horizons that can arise inside black holes, it turns out that quantum fluctuations play an important part of have an important role to play. So I'll skip over that, but maybe you'll just take that for granted that. When we consider quantum fluctuations, there's rigorous work by Stefan Hollins, Bob Wald, and Youchen Zhang that say that the quantum fluctuations inside a black hole, inside a charged black hole, change the picture considerably, because there are sectors of the parameter space where this inner horizon is classically stable, but the quantum fluctuations make it unstable. So that's the kind of scenario that we're in here at the moment. The classical perturbations, certainly some of them, don't give rise to any instability. So, well, I ticked the OR box in RQI, and now I'm going to try and tick the Q box by saying something about how quantum fields behave. Okay, and this is the bit where we should turn off the recording. Right, so I tried to figure out how you do these kind of calculations, and this is in the same territory as Marek was talking about. So it's basically looking at these two-dimensional models, it's two-dimensional effective theories of four-dimensional gravity. There are different families of these. Marek talked about the JT model. This is sort of the one I'm using due to Tomasevich and Wu is sort of a first cousin of that. So it's basically taking the four-dimensional geometry. So we have four-dimensional geometry and matter, and we turn that into two-dimensional geometry plus a dilaton plus the matter that somehow drops down from the four-dimensional case. Okay, so there's this work by Zhu and Zhang that shows in these self-similar spacetimes the renormalized stress tensor, and that's the key thing that I'm going to be interested in. This represents the actual physical content with the spurious infinities subtracted away, the physical content of the energy of this quantum field, the renormalized stress tensor. There's a nice decomposition that Zhang has proven for these self-similar fields. I don't need to worry about my radial coordinate. Rho here is log of or, just to turn the half line into a full line. Don't need to worry about that. Everything really just depends on this t coordinate that I'm using. V bar is this purely geometrical term that arises in these renormalized stress tensors that are, comes from the quadratic terms that we need to add to the action. I can calculate that. Nothing to see there. So it's this T-bar bit, and this is where we get help from Tomasevich and Wu. They use canonical quantization, they follow Wall's axioms, and they produce some formulas that I was able to do calculations with, and it turns out that this diverges as we approach the Cauchy horizon. So we can do an explicit calculation to show that this T-bar bit from Zhaang's decomposition blows up like 1 over z squared as we approach the Cauchy horizon. The Cauchy horizon, sorry, T has changed its name to Z, unfortunately. The Cauchy horizon is at Z equals Z1, so we get this inverse quadratic blow up. Okay, there's lots of open questions. The first few, so conclusions, there's one conclusion, no evidence of classical instability, but for a particular 2D effective theory, doing a particular calculation, there's an indication that the quantum fields diverge there. There's some fun mathematical problems that remain unresolved, and the quantum calculations, I think, really is the bit that needs a bit of work. Different 2D models can give different results. I don't know in particular if the four-dimensional state is a Hadamard state of the quantum field, so I've started some work on this to do a more robust calculation of this four-dimensional renormalized stress tensor to see if this is really the case, that things are happening the way they seem to be happening. Okay, so that's all. Thank you very much.
I don't need to think. So, Brian, is this divergence of 1 over z minus z1 squared enough to be worried about, to be pleased with? That's not really instability, it's just a divergence.
So I mentioned that there's a similar thing happens at the inner horizon of the black hole.
Yeah.
Okay. I don't think I used the phrase semi-classical gravity. So that calculation is in semi-classical gravity. And when they put that renormalized stress tensor into the right-hand side of the Einstein equations and work at first order in h bar or something like this, you show that you get a divergence in the geometry, a singularity in the geometry that isn't there in with the classical perturbations. So your Cauchy horizon turns into a singularity.
It does turn into a singularity.
Yeah, and haven't checked that here, but that would be my, that's the next thing to check, and I suppose I could call that a conjecture, that this does indeed lead to a curvature singularity in the geometry.
Yeah, okay, so you think it would. One unconnected thing towards the beginning of your talk, you said that you weren't considering pressure from the photon dust.
Yeah.
Is that an assumption? There would be pressure, wouldn't there?
I don't know how to model that. I don't know what that model looks like. But yes, that makes sense. I can't think of solutions that do that.
Well, I don't know anything about it. You're the expert.
Yeah, no, I don't know. Maybe somebody else knows. But yeah, I mean, so this is for null dust, so particles of dust that are traveling at the speed of light. Dust being synonymous with zero pressure. In the case of massive dust particles, when the pressure is small enough, it doesn't prevent the appearance of singularities and even of naked singularities. So you might guess then that introducing pressure into the massless case doesn't change the scenario. There are more respectable models of a collapsing cloud of massless particles. The Vlasov model, which is kind of building a sort of a massless version of of Boltzmann models of clouds of particles collapsing using distribution functions and so forth. This null dust is a singular limit of that Vlasov model, and again, these Vlasov models can form singularities.
Okay, thanks very much.
Yeah.
Yeah, so maybe just looking at purely the classical picture here on the instability. I mean, from the beginning, you're using the linearized Einstein equations, which seems fine when you're looking at the Pascal cone when it's flat. But, you know, as you approach that singularity, the curvature gets big. Is it possible the classical instability comes from the nonlinear parts
For
of the
sure. Yeah. I mean, this is it. I mean, when you do a linear analysis, your conclusion is that the linear analysis produced a certain result. And as we know, there are situations where the linear analysis gives you, let's say you find a linear instability, and that gives you a strong indication of nonlinear instability in the full system. And then there are those counterexamples where linear instability is overcome and stabilized by nonlinear perturbations. I can't think of anywhere in general relativity where that happens. And so in other matter models where linear instability has been shown to correspond to nonlinear instability, and linear stability that, you know, with quick enough decay, for example, in the study of perturbations of black holes, they're initially found to be linearly stable, and then you build a nonlinear argument that bases itself on that linear stability argument. So I kind of think a linear instability here in the context of general relativity is fairly convincing that you would see nonlinear instability. Of course, I haven't seen linear instability, but I think that's my best guess as to what would be happening there.
Do you know if anyone's worked on that? I mean, I'd be curious to see what someone's approach would be to actually to do it with the full nonlinear equations and see. I mean,
Yeah,
definitely
okay, so
a
for
taller
this-
order, but
Yeah, for this matter model, so the nonlinear work, so let's say we go outside symmetry, go outside spherical symmetry. There are solutions that are not spherically symmetric in various different classes of solutions of the Einstein equations, where we can have a null dust source, but it's not spherically symmetric, and we can get naked singularities. And that's in full nonlinear general relativity, okay? I mean, the key thing here is to perturb away from spherical symmetry, right? Because the world isn't exactly spherically symmetric, and stars, even if they're built of photons and nothing else, are not spherically symmetric. Where else might you go? You might go into this Vlasov model that I just mentioned for collapsing massless particles. There is a body of work on that, but there isn't a proof of cosmic censorship in this model, which is, you know, the ultimate goal, showing that if naked singularities do appear, they're unstable. There are proofs of this statement for other matter models, but not in the ones that are most directly related to what I'm talking about here. I mean, that's also a get out of jail clause here is, well, who's ever going to see an actual physical object that's built of a cloud of photons that are collapsing without pressure and so forth? The Vlasov model has nicer mathematical properties, and I think everybody believes that this will be shown to satisfy cosmic censorship, but there isn't a proof. This is a hard problem. Other matter models, it's been proven for, but not Vlasov. Yeah, I mean, there are results on Vlasov which give an indication that it's. I think people believe that it's true, but I don't think there's a proof.
Right. Oh. Yeah, go for it.
Possibly my question about the very start. Could you explain what it is about the kind of thick shell that means that C plus is not like the same as the horizon? Why is there a bit of a gap there?
Okay. Yeah, good question. So let me go back to that. Okay. Okay. So when we put in this cutoff, so this is the region that's filled up with the collapsing shell, the collapsing radiation. When we put in this cutoff, we get the Schwarzschild solution outside. So basically what's happening here is that the shell is collapsing down. It collapses down to 0 radius. And the Cauchy horizon, another way to define the Cauchy horizon is it's the first light ray that escapes from the singularity. Okay. And what the diagram is showing us is that this light ray escapes, so it escapes from the singularity, and then it escapes from the surface of this star that's built of photons. So it's into the Schwarzschild region, and it got out before the event horizon formed. So that's why we have this difference here. And it managed to get all the way out to infinity. But in fact, there is a slight peculiarity of this model, which is that I could colour in all of this in grey and it would be the same picture. The outline would be the same. So the radiation can extend all the way out to infinity. The reason for that is basically because in the metric we have m over r. So even though m is varying, when r goes to infinity, it drops off to infinity and drops off to 0 and it's asymptotically flat. So it doesn't make a huge difference. So the key thing is not so much that this photon can escape the sphere, it's that it can get to infinity before the horizon, before the event horizon forms.
Thank you.
All right, let's thank.
Another question, if there's time.
I am a physicist. Yeah, just about that diagram. How come it goes to the left? I thought isn't like r equals 0 like the center? So why does it keep going to the left?
You're talking about this here?
Yeah.
Yeah, good question. Yeah, these diagrams are a little bit mysterious. So the reason for that is that as we send photons in, and remember, so the rule for these diagrams is that the photons that are moving in radial directions are straightened out to plus and minus 45 degrees. Okay? So light rays moving outwards are going like that. Light rays moving inwards are going like that. Okay. And when we write down the equations to describe the propagation of these light rays, we find that there is exactly one here on C minus that reaches and this turns out to be V equals 0. So we have V equals 0 going all along there. V equals a tiny bit bigger than 0 are always going to end up at or equals 0 up here. Okay? So we have this picture along here. And then for the outgoing ones, we find that we have these ones coming from or equals 0. And then we find that we get these ones coming out of V equals 0. So the only possibility is that the diagram must look like this.
Okay.
It needs a little bit of thought, but that's it. It's basically, so we go to the geodesic equations describing the propagation of these light rays. We've straightened things out, and it must look like this. So if it were vertical, there would be other incoming ones that hit it. Okay, so it can't be vertical.
Yeah, okay.
And it can't be anything other than 45. It can't be over here either, because then there would be other ingoing ones that start there. It can't be here, must be here.
So it's kind of the fact that you're talking about photons collapsing again, the kind of that the fact that it's a bit of a toy model, that it has to do that because photons have no mass, so they have to behave like that kind of thing.
Yes and no, and maybe we'll talk about it afterwards, and I can explain why even massive particles could give you a picture like this.
Oh, okay.
All right, let's thank Brien again. And lunch is downstairs. If you haven't taken a photo, look forward. So welcome back. This is going to be our afternoon session where the talks are largely going to be about causal set theory. But at the end of this, before the coffee break, there's going to be a general discussion and question session. So if you have any questions for the earlier speakers or any questions come up, keep them in mind, write them down, and we can come back to them. But right now, let me introduce Liam, who is going to be talking about why causal sets.
Thank you, Josh. Hi, guys. So my name's Liam, and my advisor is Dr. Yasaman Yazdi here. I'm currently doing my master's or finishing it up in Trinity. No one actually teaches causal set, or no one actually researches causal sets in Trinity, but I was really insistent, and I asked special permission if I could come to DIAS and I could work on causal sets. And I'm hoping that at the end of the talk I can kind of share why I was so interested in causal sets. So causal sets is a theoretical framework that we're hoping leads to a nice theory of quantum gravity. And I think the most important thing I should say about it is that it's a discrete theory. It makes this core assumption that the background of space-time, right, is fundamentally discrete. Now, it's not the first time people have thought about a discrete background. I mean, this is an old idea. It goes even back to Riemann. There's some notes he makes about this idea of a discrete manifold. Now, he never really formalized what he meant by discrete manifold. Now when we move further into the 80s, and there's these ideas of cellular automata. Even 't Hooft actually has a book he published in 2017 on the quantum mechanical approach, or the quantum mechanical understanding of a cellular automata, and he has this kind of idea, this like framework there to understand some discrete object. Now, causal sets is unique, and I kind of will talk about why it's unique in its approach to this discrete background in the following slides. But I think to really motivate it, okay, we have these fundamental objects, okay. So sorry, yeah. So let me just sorry, I'm a little nervous. Give me 1 second to recalibrate. So the first thing I want to do is give you my motivation. I want to kind of give you what we do sort of know is true about causals, or is true about physics, or we see these problems with quantum gravity, right, that remain unsolved or remain sort of mysterious. And then I want to just give you a brief introduction to the actual objects, okay? So if we kind of go through a list, the first almost immediate reason why people started talking about, this pixelation of the background was the Planck length, okay? So this idea that there's some minimum length, okay, if you in your head you think about, okay, let's just assume that there is some minimum length below which measurements don't really have a meaning. What does that fundamentally mean? Well, if you go get a piece of paper and you draw a background, you draw a manifold, draw your favorite manifold, and you draw a length, you'll realize it's going to chop it up into pieces. Okay, it's going to chop it up into these discrete chunks, and so you can kind of imagine that throughout, as we're developing our theories and we're getting more rigorous, and we have this like remaining problem with the Planck length, we can imagine that there's some naive approaches to discretizing space. And I do want to touch on, actually, because I think it's important, why this sort of just naive, take a smooth manifold and chop it into regular pieces like you do to solve a numerical problem, don't really work, okay? The other thing I want to talk about, and this is actually something that the people that follow me will be able to give in more detail, is UV divergences, and singulars and GR not so much, and entanglement entropy in particular. And I think that's kind of what a lot of people here will find most interesting in the following talks. I also want to kind of, this is a nice way to frame the problem, or to at least kind of let us open our minds, because in your standard course in undergraduate physics, you'll spend a lot of time with analysis, you'll spend a lot of time with continuous objects, and you'll use some very sophisticated tools, right? And there isn't as much, I think it's fair to say that the discrete mathematical world and finite math work is not as sophisticated as the continuous mathematical world. And in our standard course in undergraduate physics, we don't study graph theory, we don't study combinatorics. You might, but it's not your standard course, okay? But maybe in 100 years it might be, I don't know, okay? And then I want to then move on to this theorem, the Hawking, King, and McCarthy-Malamud theorem, which kind of also gives us why Well, it's going to tell you how, one, you recover the causal structure of the background, okay? And two, what you pick up from it being discrete. And that is this volume counting correspondence. You automatically get the volume for free just by counting the number of elements. Because you have a finite object, a structure that's made of finite elements, you just need to, it's a counting problem. So a lot of stuff devolves into combinatorics. Okay? So, the Planck length. So we actually had John Nash talked about this earlier Charles Nash, the Planck length, okay? I think what's quite fascinating about the Planck length is if you do try, let's say, okay, I do try to make a measurement. I take some photon and I decrease its wavelength down and down and down and down. It's a known result when you do that, I mean, the background pushes against you, okay? An event horizon forms, there's a collapse into a black hole. And so there's this fundamental property that we can kind of understand somewhat classically is forbidding us to measure distances below the Planck length. But we're not saying, okay, maybe it just breaks down. We're trying to motivate a framework that doesn't break down fundamentally, that the Planck length is some fundamental object, and the breakdown that we see in our semi-classical theories is just because the approximations we're using to understand GR and to understand quantum mechanics aren't the true fundamental, they're not the fundamental structures. We're superseding, we're usurping the manifold here and replacing it with a graph, right? That's really at the core of what we're doing. We're building, or hoping to build, or we are building a theory based on a completely different object than most people are familiar with. So I'm hoping, okay, that I can further motivate this, okay? So there are two things that most people here will be familiar with, right? And that is going to be doing some QFD calculations. You have to impose some UV cutoff to make a lot of your loop integrals work. Why? It's a good mathematical trick. It gets you an answer. You go and you solve these integrals and you go to CERN and you look at scattering experiments, you get the right answer, okay? But why is the UV cutoff necessary? Is it just a mathematical artifact? Well, causal sets gives it not just a mathematical artifact, it gives it a physical motivation. There is going to be UV cutoff, and it's necessitated by the fact that the background is discrete. And it's no longer just this, it's no longer a mathematical trick that allows you to get good answers. It is a necessity, okay? It's a necessity from the theory. And then we also get to a nice property in causal sets where you're able to avoid singularities. Now, obviously, a very important one would be like the Big Bang singularity. If you imagine, I don't think there's many people that genuinely believe that if you rewind, time all the way to t equals 0, there's actually a genuine singularity at the beginning of the universe. I think almost everyone would agree that there's some breakdown in the quantum gravitational regime that we don't fully understand. Now, causal sets avoid singularities. Well, it avoids singularities because you'll never have an element get generated on a singular space if you have some, this is your central line of a black hole, it's your singularity. The probability density of a point being there is 0, right? There are other things, though, that are also problems, but I think that maybe we'll talk about maybe in a future talk or something, that there's some interesting graph theoretic properties that happen around singularities, but you don't get singularities in the sense, you don't get singularities in the sense of this breakdown of curvature, okay? So I mean, that's quite interesting, I think. Okay, this is maybe a heuristic argument, but genuinely say, okay, let's go from the continuous point of view, and let's say you try to take a measurement of a continuous variable, and you need to distinguish it from another measurement of another continuous variable. Can you try and imagine a system, some physical system that you can construct to distinguish between the two of them? How are you going to store that information? Is it going to be a string of electron spins that encode the thing? There is, as far as I've heard, I've never heard someone give a really convincing way to store, represent fully a continuous variable. And that's because inside it there's, a divergent amount of information, right? So the other thing that's, I think, very familiar to a lot of people, this goes back to the UV cutoff, is that the entanglement entropy diverges, okay? So what I'm trying to get at here is that
I mean, this is maybe more of a belief at the moment, but that in a finite amount of space-time volume, you're probably going to have a finite amount of information. Now, maybe that's not the case, but it's certainly the case that if you have a non-finite amount of information in a physical system, there's no way to verify it. There's no way to actually measure it and say, oh no, I have this continuous variable here. But there is, as a matter of fact, a way to do it if it's discrete. If you're able to measure directly, say, a causal set element, I don't know if that's probably energetically possible, probably isn't. But if you were to, that would be, a distinguishing feature and say, oh, you'd be quite certain. In the same way that, I'll talk about this now. Same way that we think about matter, right? If you go back and you look at early discussions about what is matter and stuff, they speak about it as, there's two camps. It's made up these discrete objects that are filled, that we now call atoms, and there's also this continuous argument. Because, if you look at this table, right, it does look continuous. We do know, but we know that we can actually get the volume of this table just by counting the number of atoms in it. And it's not necessarily a necessarily strong argument, but it's a very good analogy. If you're coming from the continuous world, it's a very useful tool. It's a very useful tool when you're getting kind of lost thinking about causal sets to keep going back to it. It's a great touchstone because I think every physicist does sort of understand this idea, okay, I have a large collection of n objects, the n is astronomically large, and I zoom out, it does start to look continuous, okay? And this is a great touchstone analogy for when you think about, okay, how does this look like a manifold? How does a collection of vertices and edges actually look like a manifold? Come back to the atom analogy as often as you can because I think it's quite a useful touchstone, right? So, this is the same information argument I made before, right? So there's a nice argument by Sorkin where he does talk about directly verifying that the background is continuous. And he makes this nice argument that there is no set of experiments that you can conduct to prove it, but there is a set of experiments in principle that you can conduct to verify that the background is discrete. So take with that what you will. Okay. So now the point I want to come back to is, okay, let's say you're thinking of the universe as discrete and you're constructing some naive theory of it. The first thing you do is go along the coordinates and just block them out, right? You make a regular lattice. The problem with a regular lattice is, first, if anyone has done lattice QCD, you know it immediately breaks rotational symmetry, right? If you have a regular lattice, you only get valid rotations that are rational numbers. So if you move 5 elements up, 3 elements up, any irrational number in between that doesn't have a rotational representation. The second thing, it's a little bit more subtle, is you break your boosts, your Lorentz boosts. That is a little bit harder to see, but it is at the crux of why you necessarily need a random sprinkling. Okay, so first you can kind of, I think, intuitively understand the rotational. You can understand the rotational invariance that gets recovered in the large n limit. The idea being that you can come up with some, say, rotational axis, and there's a non-zero probability that there'll be a vertex there. If you do it in the fixed lattice case, you will be able to find angles that do not have that have a functional zero probability. So causal sets only becomes, Lorentz invariant in the large n limit. It becomes it in a statistical way. But I think what can also happen when you think about causal sets is we get hung up on the sprinkling process. So anyone that's done some causal sets knows that we have a nice way of generating manifold-like causal sets. We take a manifold that we know, and we generate points on it that are distributed so that you have the expectation value of the number of points is equal to the volume, and then your density determines your length scale. But that's the wrong ontology. That's going from a manifold to a graph. That's fundamentally the wrong ontology. What we're hoping to do, and it's a much harder problem, is to go from the graph, what are the rules at a fundamental level of this graph, and then say, okay, this is the space of manifolds that it generates, or I should more specifically say, approximates, right? And then you recover the physics, okay? So it's important to have your ontology in the correct order, okay? So right? So there are other approaches that are still actively studied. So all kind of the ones from the 80s, these discrete lattice ones, Edward Fredkin comes to mind. These are somewhat abandoned for those reasons, these Lorentz invariant problems. The ones that do remain are loop quantum gravity, okay, which is distinct in that it has a discrete space-like structure, right, on these hypersurfaces, but the time component is fundamentally continuous. Causal dynamical triangulation is close. I think it's maybe the closest cousin to causal sets, but it fails. Well, it's ontologically different because it uses the discreteness as a tool, but then claims that the physics is only recovered when you take the density to infinity, right? So it's distinct in that capacity. Causal sets is kind of your only currently, widely studied theory that fundamentally treats each element as a fundamental object. This is the building blocks of causal sets. They are these discrete elements that have a connection, a causal connection, and that's it. And in many ways, actually, the simplicity of what a causal set is a useful part of its beauty, because it's a great jumping place to build something on top of it, right? It's got a low barrier to entry. I think most people spend a little time, they can draw dots on a graph and they can connect them and they can, find arrows. But it's also rich. So it's surprisingly rich given how simple it is. And I think that's also why, because originally when I kind of came into sort of this, like thinking about, a background that's discrete, I mean, my first instinct was to draw some pictures and stuff and whatever. And I did remember kind of seeing, this is some problem with, Lorentz invariance. How do I make my tiling in such a way that I can tile it? And the reality is you don't want to tile it. You simply do not want to tile your manifold. You want to make something that isn't a tile. And I think that's quite fascinating because it solved the problem of how do you have a nearest neighbor that's on the other side of the universe, right? If you go along a null line, you're basically, only a distance 0 or something quite small. At tiling, there's no tiling that exists. And I have to be careful saying that. There's no tiling that exists that has that property, as far as I'm aware of, Okay, so why causal sets? What is a causal set? The definition is quite simple. I do want to point out these conditions here are all the same as you would find in a Lorentz manifold, right? You've got your order relation, you've got this reflexivity property, and you've got acyclicity. Now, maybe I'll put an asterisk there. You can enforce, you can find solution signs and field equations with loops and stuff, time loops, but for the most part, these are all the same as the continuum. The distinction is here, okay? The distinction is defining this Alexandrov interval, right? So really simply, between x and z, there are 4 elements. The only extra condition we impose from the continuum is that the number of elements, the cardinality of this interval is going to be finite. That's it. Okay? Is that enough to get the richness of GR? The claim is yes. The claim is yes. So Hawking, King, McCarthy, and Malamud, who are pictured here, okay, have a nice conformal, nice paper on conformal symmetry where if you have your space and you have the causal order, so I've represented it here, just the causal order, you know the structure of the space up to a conformal factor, okay? So you're able to know what the geometry is and then scale it up or down. If you add in a sense of a local volume element, then you've got the entirety of the manifold. You've got the manifold and its metric. And causal sets, if we go back one slide, okay, the ordering is baked into the definition. So you'll have this set of points and it'll have some order connection. But you automatically also pick up the volume element just by counting, okay? The amount, the idea is that, inside this volume, you count, 4 elements or n elements. It immediately gives you the volume. So you automatically pick up the conformal factor just by nature of being a discrete object, discrete and finite object, okay? So some objects that, are useful and I think are nice analogies, right, is, these are the smooth manifold connection here, and this is just the example in causal sets. I think what I'm hoping to get out of this talk is that you get a picture of what we've got structurally going on. So you can generate this. We know quite easily how to generate this from that. Ironically, you tile your diamond, and then you assign a probability that a point gets generated at each tiling. Now, it's not so clear how you go back, okay? But the idea is that we define what it means for a graph to be manifold-like by its ability to be embedded into a manifold, okay? So if you, but the problem is it's not necessarily easy if you have, say, 10 to the 7 points going and actually one by one trying to embed it back into a manifold. So we have workarounds to figure out what the dimensionality looks like. So some other objects, okay, I'm going to introduce these quickly, is causal matrix. So you can take that in, that ordering, and you can just embed it into an m by n matrix, and you can do similarly for links. Don't think I need to go into that too much. Okay, so back to the sprinkling. So the Brosnan, I think most of the people are grasping kind of what we're doing here with sprinklings, but I just want to come back and reiterate this as you go into the next talks. The sprinkling process is not a fundamental process. It's a testing tool for us to generate useful causal sets that we already know are going to be manifold-like and that they embed. And then we're going and looking at those properties at a graph theoretic level, and we're hoping to see how are they distinctive from non-manifold-like causal sets. Okay? So, of course, there's geodesics. That's just, you just go through a chain. If you go through your causal matrix, you find the next element that's order to it, and you can generate chains. I'll briefly talk about some dimensionality estimators. There are, they basically count the number of, if we go back, the abundance of chains, right? You'll find actually in the causal matrix that it gets sparser as the number of elements increases. But no, by counting the abundance of chains, there are dimensional estimators. Now, I'm currently working on something, and I think I have a slightly faster and slightly better way to estimate the dimensions that considers just boundary points. And it's interesting that I think hopefully I'll be able to talk about this in the future, how going to just the boundary points gets you a quicker estimator. All right. Okay, so I want to just conclude so it's actually it's already known that there's enough richness in a causal set to recover GR. We actually have an action. We actually already have an analogy of an Einstein-Hilbert action. And it's simply defined as essentially going through the bulk and counting the number of chains. And it's interesting that just an alternating sum of it is sufficient to recover all of GR. This, I think, is quite it's quite fascinating that all you need is an alternating sum. Now, this isn't just one. There's actually an entire family of chains. So of chain lengths, counting how many chains are length 5, length up to length k, right? But it turns out that this is the smallest you can make it. You need at least, if you think about it, you need at least maybe 1 hop to get a derivative, 2 hops to get a second derivative, and 3 hops to get nth derivatives. So if you start calculating something in GR, you want to get the Ricci scalar, you need there's a certain cutoff on how many hops you need to actually define what it means to have a derivative. Okay, so the last thing I want to talk about then is the stuff that I'm working on is, okay, the space of causal sets. I've kind of been keeping this from you. The space of causal sets itself is dominated by things that we know manifestly are not manifold-like. These are Kleitman-Rothschild orders. They're simply 3-layered graphs with interconnected values. It turns out when you get to about 10 to the 7n, almost 99% of causal sets are these KR orders. So the problem then becomes, okay, well, how do we tame this, what seems to be a huge entropy problem? And I have some ideas, but I mean, the first thing you'll notice is that these are highly connected. So it's almost like everything in the space is next to itself. And this actually kind of might be a good model of what the early universe looks like. So rather than going to a singular point, we actually just have this large collection. You can imagine this n goes to, millions and millions. It's 3 layers, but it's extremely wide. There's a high number of points, but they're still extremely connected, right? So you still have this large space of points that are well defined. Okay, so I'll give some properties of them. Not too important. So that's the current research aim. But I kind of want to talk in a wider context, specifically about ever-present lambda, which is a lesser-known result. And I do wish I probably should have put a slide in. it's a lesser known result, but it should be a much better known result, because in the 90s, Sorkin has a paper where he estimates what the order of magnitude of dark energy should be, or the cosmological constant should be, and he finds that it should be something like 1 over square root of n, where n is the number of elements in the past. Okay, so you take the volume of your causal past, you say that the sprinkling is on the order of the Planck, some Planck volume, so 3 Planck lengths in a Planck time, and you just divide and you get an n, you get a number. It turns out that, and so his argument is that it's a statistical fluctuation, dark energy is fundamentally a statistical fluctuation on the order of 1 over square root of n. What's so fascinating is that it was correct. So we talk about, good theories of quantum gravity. They should be testable, they should have testable prediction. Causal sets already has one, and it was right. His order of magnitude nailed it on the head. So I'm surprised it's not as well. When I found out about this is not very well known. So it's already, I might be getting in dangerous territories here. It's already got a testable result over string theory, which has been worked on by thousands and thousands of very intelligent people doing very intelligent maths. But and it's suggestive that something, one of the interesting things about it is that in the very early universe, it predicts that the fluctuations are so big because n is so small that the cosmological constant goes negative at some point. If the data comes out that it happens to be that it goes negative at some point, that's kind of a clincher. I think that'll be pretty much end of the road. Everyone will be like, The other thing that's a nice property of it, because it's a statistical fluctuation, it has a small variance, right? So it moves. So you're getting new cosmological data coming out. Experimentalists are saying, some good theorist should come out and give an explanation for why dark energy should change a little bit. In the 90s, it was already part of a prediction. It's already baked in. You actually can't remove the small variation of the cosmological constant because it's a fluctuation. It's tied into it. So, and the other thing is, what about fine tuning? What if I want to change the order of magnitude? If you want to fine tune the order of magnitude of the cosmological constant, then you have to give up that your argument is that the pixelation of the universe is at Planck order. The fundamental assumption is that the number of points is some Planckian volume, and you divide the past space-time volume by it. So the fine-tuning is quite constrained. You can maybe change the first few digits, but the order of magnitude is more or less fixed. So, when I heard that, I was, there's something to this for sure, and definitely worth researching. Any questions?
Question?
So you mentioned the dynamics, the action, right? The action can be rephrased in terms of counting vertices and points and things like that. So say that I rewrite the action like that, how do I get dynamics out of it? Because say in space-time, it's sure, we have the Einstein-Hilbert action, but we know how to rewrite that in terms of equation of motion, and given initial data, we can solve it, right? Can you do something like this in causal set theory too? Like from this action that you mentioned?
Dynamics is currently an area of active research. So I'd conjecture probably. There are these classical growth models that you can take, so they work by growing element by element. And you, in principle, could take the action and say, shape that as the way it grows. Is that the best way to do it? No. And I also want to caveat that it's not just counting the number of elements. It's very important, actually, that it's not the number of elements. It's the number of specific subgraphs. It turns out, actually, if you just count the number of elements, you don't get anything useful. You need to be counting subgraphs. So you need to be counting structures. You need to be counting how many times do you see something like this show up. Their one was just chains, right? Their one was just counting the abundance of chains. But there's a nice entropy argument for why just counting the number of points gets washed out by the Kleitman-Rothschild orders. Faye Diper has a good paper on that, which I can refer you to. So it's important that it's actually counting the number of subgraphs. And I think that's actually illustrative of kind of what's the next for causal sets is, instead of having a growth model that adds a point at a time, we should be adding subgraphs, okay? Like, why should one side of the universe have to wait for a point to be generated for another side? It should be happening, there should be some level of multiple points being added at the same time. So to answer your question, the dynamics are still under development, but hopefully we'll get some.
I think we will save any questions just for the discussion session, just also because there are a bunch of causal set theory talks back to back. So please thank Loom again. You're we'll just take this and clip it to there, or your pocket will also work.
Is that good? Okay.
Our next speaker will be Thomas, who's going to be telling us about causal set propagators in de Sitter spacetime.
All right. Assume this works. No. Do I need to plug this in? Yeah, that would make more sense. Yep, that would make more sense. Okay. All right, very good. Thank you, Josh. All right, so hello, everyone. So what I'd like to talk about today is a bit about how we can formulate quantum field theory on causal sets and some of the kind of interesting ideas, being the SJ vacuum that have come out of that, and how about we can go about studying quantum field theory on causal sets in de Sitter. All right, so what's our motivation? Many people have been thinking about the kind of discontinuity between how gravity and quantum theory fit together. So our motivation for looking at this is obviously causal set theory is a direct approach to doing quantum gravity. And at the same time, we're also kind of probing this kind of semi-classical approach of just doing quantum field theory in a curved background. So these sort of ideas have led to a lot of good theoretical results, as have been mentioned a lot today. So stuff like Hawking irradiation, the Unruh effect, and quantum perturbations during inflation. So when we look at these sort of things, one of the central ideas that comes to affect doing quantum field theory is the vacuum. As often when we're doing quantum field theory, the simplest case is to start out with your theory in the vacuum and to study it like that. But in the case of, let's say, Minkowski spacetime, there's a very natural choice of vacuum. We expand our field over the modes that are solutions to the KG equation, and we define the vacuum by saying, okay, this is the state that our creation operator, or an annihilation operator, will annihilate. But when we go to curved spacetimes, this notion of vacuum kind of breaks down. There's this notion of this notion of vacuum being the same everywhere breaks down. Right? You may have that in a certain coordinates, the creation annihilation operators may have non-trivial relations, such that if I am to act on, let's say, the vacuum that is very close to a black hole, with the creation annihilation operators of an observer very far away from the black hole, I might end up creating particles out of the vacuum, and that's kind of what we get with Hawking radiation. Okay, and yeah, so different points of space-time, especially when it's curved, can have different notions of creation annihilation operators. Okay, interestingly, through the study of causal set theory, a covariant way of defining a vacuum for a globally hyperbolic region of spacetime was found, and is known as the SJ vacuum or SJ state. And that's hopefully what I'd like to introduce a little bit today. Okay, so first let's go through a bit on causal set theory. Thankfully, Liam has gotten through a lot of this, so I can speed through a lot of this. So we have these 4 properties, and with the main point being that causal sets are discrete and they preserve causality. Okay, so now let's look at quantum field theory. So we want, in the usual case, when we do quantum field theory in the continuum, we're going to have some Lagrangian, which will give us some equation of motion. And for the simplest case, I can take a free scalar field. So I'm going to satisfy the Klein-Gordon equation. We then quantize our field in the canonical method, where we take our field and our conjugate momentum, and we impose that they're equal to this. And then we get around to the notion of causality by having that the commutator of the two fields at any 2 points will vanish when these points are space-like separated. So I'm basically saying, if I make a measurement of my field at a point x and then a point y, this should not be any different to first measuring y and then x if those points are causally separated. There's any sort of propagation could not have taken place. Okay, so with this function then naturally leads us to our Green's functions for telling us how the probability of propagating between 2 points, and they satisfy these equations. Okay, they'll be useful later. Okay, now on a causal set, things are a little different. We're not going to have, because we are in a discrete setting, we're not going to have this notion of a differential equation as cleanly. So it actually serves as, it is actually a lot easier to formulate in terms of some different quantities. So what I can do is actually take this commutator function directly, and based on my knowledge of before, I can define it as being equal to the difference of these two retarded and advanced propagators. And the reason this is useful is because these are quantities that are very well known on the causal set. Okay, as we will see in a minute. Okay, and then we'll see later that this Pauli-Jordan function, this delta xy, can be used to construct important quantities, such as the 2-point function. And for a free theory or quasi-free theory, that's going to tell us everything we need to know about our quantum field theory. Anything we want to calculate, we can get out of that. Okay, so Lima also introduced these quantities, so this is good. So one of the most important quantities is this causal matrix, which tells us basically everything about how the points in the causal set are causally related. Okay, to see how we can use this to get a propagator, we can just work in 1+1 dimensions. And now if we can think about, so we want our propagator on our causal set in the continuum to look exactly like our the known Green's functions that we know very well from continuous 1+1 quantum field theory. So if we consider the continuous version of this function, it's going to be basically a 1 in the feature light cone and 0 everywhere else. So this feature light cone has value of 1 and 0 everywhere else. Okay, and then if I want to write that down mathematically, I would have to write it like this. This imposes that I'm within this triangle as the proper time becomes imaginary outside, and this heavy side theta function imposes that I'm in the feature light cone, not the past one. And you may recognize that this quantity here is exactly half the massless Green function in 1+1D. So if the continuous version of this function matches the continuous Green's function, we can postulate that on the causal set, we can just use, up to a factor of a half. That's why this factor here, we can use this as our propagator. Okay, so that's specifically in the massless case. In the massive propagator, there was a proposal by Johnson that to obtain this, we can use a sort of hop and stop model. Let me get to the images because I think these make more sense here. Okay, so if I want to know basically the probability of going from one point to the next, a way of generating this for a massive propagator is to consider basically all the paths between those 2 points and to weight the probability of stopping at each of these points by something that we find out is proportional to the mass. This is actually very similar to something we do in regular quantum field theory. Usually we just write down a Lagrangian and we work straight away with the massive propagator. But if instead we wanted to treat our mass term like an interaction, then we could find that, okay, if I have the probability of going from here to here, then if this was an interaction, I would have this diagram of just going from point to point, but I'd also have a diagram where I stop, or I have an interaction, because the mass term is phi squared, this will only be a two-leg interaction, and then I can keep going. I can have as many stops as I want, and I'll get a geometric series exactly like this, and I'll get the massive propagator. So it's actually very similar to something like that. Okay, now let's have a look at the SJ vacuum. So the Pauli-Jordan function is, when we're working in the causal set, is now just a matrix, because it depends on the field at 2 different point values. So it is also an anti-symmetric matrix and Hermitian, which means we can expand it over a basis of eigenvalues exactly like this, where, yeah, these are expanded over a basis of eigenvectors, which will look like this with some eigenvalues lambda I. So if we want to pick out a specific, okay, it is very noteworthy that we can, out of this construction, we can write down some quantities that can be shown to satisfy these computational relations, exactly like creation and annihilation operators. And then what we can do is we can write the field in the usual way in terms of these creation and annihilation operators. And then this is all consistent such that plugging this into the definition of the Pauli-Jordan function will give us that, that function. Okay, so now what's very interesting is, as you recall from my definition of the vacuum, as soon as I write down a creation and annihilation operators, I have actually picked out a preferred state. And that state is exactly what we call the SJ vacuum. Okay, so we can then, as I mentioned earlier, we can go ahead and calculate this two-point function. And if we plug in the definition into the vacuum, so A is defined to annihilate this vacuum. So this one is going to annihilate this, and this one is going to annihilate this one. So I only care about these two terms here. And yeah, using the relations of the creation and annihilation operators, I basically end up with this quantity here, which if you recall from the last slide, if I just take the u's like this, it's basically this first half of the Pauli-Jordan function. So how we more generally define this SJ state is we can say it's the positive part of the Pauli-Jordan operator. And that's very useful. So this procedure was found on a causal set, just like I've kind of constructed it, but it can also be extended to continuum spacetimes. Now, in the continuum, delta is a function, not an operator like it is when it's a matrix. So we're going to need to, so what's needed is, you can use it as the kernel of an integral operator that acts on some functions. So then you're going to have eigenfunctions, and once you have eigenfunctions and eigenvalues, you can construct a continuous SJ two-point function from the positive part of this operator. Okay. So let's look at de Sitter. So, sorry, did I mention that later? Yeah, no, that's fine. Okay, so let's a little recall on de Sitter spacetime. So it's nice to visualize de Sitter as this kind of hyperboloid embedded in Minkowski. So for example, this is d equals 1 plus 1 de Sitter. So I'm saying I'm living on this sheet, but it is curved in this extra dimension so that I can really visually see what's going on. And then if you want to really talk about observers, it's much more convenient to choose a slicing of this space-time. And then this looks exactly like a sort of FLRW space-time, which we're very familiar with, and it just kind of describes a homogeneous space-time that is expanding. So de Sitter is very nice to study, as has been mentioned. It is the same amount of isometries as Minkowski space, but it's very non-trivial in that it depends on time. It's not static. Okay, so when we go to curved space-time, a couple of things about what we said about Q of t is going to change. We're going to have to, in the usual way, change our partial derivatives to covariant derivatives. And our green function is our Green's functions are going to satisfy a slightly different equation involving the metric determinant. Okay, yeah. Here's what I wanted to mainly talk about. The very interesting thing is that the definition of the Sorkin-Johnson state that I wrote down before remains the same, and reduces to a lot of familiar vacuums that we're already familiar with. It reduces to the Minkowski vacuum in Minkowski spacetime. If you have a static metric, you can define easily a Hamiltonian because you have a Killing vector that's always time-like, and the ground state and the SJ vacuum can be shown to be the same as that, the state that minimizes that Hamiltonian. When it comes to de Sitter, this is going to be a little bit tricky as to what vacuum it's going to correspond to. So that's kind of a question we want to answer. Okay, so in de Sitter, you can find a very natural vacuum just based on what coordinates you're in. The 2 coordinates I introduced earlier, you can find a vacuum just in the usual way. You solve your equation and you expand over the modes, and then those creation and annihilation operators define your vacuum. But the thing is, because of all these isometries, this is not going to be unique. I can always get my modes and write them in terms of the same modes and their conjugate, and because the Klein-Gordon equation is linear, these will also be just as valid solutions. The only thing is that the creation and annihilation operators will be related in some non-trivial way. So it turns out in de Sitter spacetime that in order for these to satisfy all the isometries, these coefficients have to take a particular form that looks like this. So basically there's a 1-parameter family based on some parameter, some constant alpha, and alpha is continuous, so I can run through continuous values and I'll have many, many different values. A natural kind of idea would be then that maybe this Sorkin-Johnson vacuum will correspond to one of these alpha vacua, with alpha equals 0 being the regular Bunch-Davies vacuum that we're quite used to. Okay, so yeah, which of these is going to correspond to? And the answer is, well, it's going to depend on dimension, is what we've seen straight away. So the first of all, we can look at simplest case, 1 + 1 dimensions. Now here, something interesting about 1 + 1 dimensions, which is why I believe a lot of why string theory is done on a world sheet, is this, is that this is my D'Alembert operator in curved spacetime, but for a conformal metric, so that's just a metric that's basically proportional to the Minkowski metric with some other scalar factor. You can write a lot of matrices like this, including my de Sitter in 1 + 1D anyway. When I write it in these coordinates, I can basically manipulate this, and I'll have a factor of omega to the d - 2. So in 2 dimensions, 1 + 1, this is going to vanish, and I'm basically left with something that's proportional to my original Minkowski operator. So what that means is I can just use my Green's function from flat space in de Sitter in this scenario. Okay, so you can then go and test that. We can get a causal set. We can use the formulas I've outlined above, and we can calculate the value of the 2-point function for a causal set sprinkled into the de Sitter spacetime, and then you can plot it. So those are all these blue points. So I'm looking at my causal set. I'm calculating for each value, for each point on it, basically the 2-point function between it, and I'm plotting it as a function of proper time. So basically how far they are separated, and then I can plot this against this continuum orange curve, which is this well-known continuum calculation that we know from Q of t, and we can see how that's related, and we can see it works very well. The causal set follows it really well. Okay. This was then extended to 4 dimensions where we live by Yasaman and some collaborators. And beyond 1 + 1, it's not as easy. We can't just go ahead and use this, the flat propagator anymore. Things are a little more complicated. And what was found is that interesting, the Sorkin-Johnson state does not match any of the alpha vacua. There's a number of reasons this could be. It could be the case that we do not have enough kind of basically computing power to sprinkle that many points into a 4-dimensional volume. But that is maybe, well, as is shown in the paper, it's the plots do seem to converge for an increased sprinkling, so that's probably not the case. The other possibility is that this is true. The SJ state does not match any of the vacuum, and is because the SJ state is kind of defined in this discrete way. It may be the case that taking the continuum limit, or taking the size of your region you're applying it into infinity, may generate states that are not exactly the same as the continuum. Okay, so what I wanted to do was to kind of fill in some gaps and look at d equals 2 plus 1. This is a little harder than d equals 2 and d equals 4 because there's not as nice of a causal set propagator counterpart. In d equals 2, we had that we could just use the causal matrix. In d equals 4, Lee-Maltry introduced the link matrix, so we can use that in its place. But in d equals 3, there's kind of not been a suitable counterpart figured out. A utilitarian approach is we can just write down the known answer, and we can basically plug in the times on our causal set. So in de Sitter, there's this nasty expression for the 2-point function in terms of the hypergeometric function. Very messy. But the important thing is, yeah, we can use this. So the only question is, what do we use as our proper time as our causal sets? And there seem to be 2 possibilities. So one is the volume proper time. So what we're saying here is that the causal set contains in it information about, if I have 2 points, it contains in it information about the volume of the causal diamond of this 2 points. And if I know the volume, and I know in de Sitter how large a between 2 points of causal volume should be, then I can immediately invert, given the volume on a causal set, inverse the expression to find tau. And then I can plug in tau into my 2-point function, and I can plot it. This didn't turn out to work very well, because it seems, my understanding of it is that it didn't work for very small tau, and the 2-point function seems to very sensitively depend on small tau. So another method of doing this is to look at the length of the longest chain. So this one's a little weirder, but if I have a causal diamond like this, something that will not look like a geodesic is something that travels, for a massive particle, is something that travels very close to the speed of light. And that might take a path that looks something like this between them. And what you'll notice that if there's loads of points in my causal diamond, this one took a path that passed through basically the least amount of points possible. It went to very close to the edge of the light cone and back up. Whereas if one was to go through the middle, you would have to pass through way more points. And that gives a notion of more straight geodesic. So that kind of motivates the idea that the most geodesic-like path is the one that takes through the most points. And this is something that's actually contained in the information of a causal set. So we can go through and we can basically, for each 2 points, see what is the longest path between them, and we can use that as our proper time. And that actually worked a little better. Okay, so here I have 2 plots of what these look like. Volume proper time is in orange, and the length of the longest chain is in blue. The volume proper time is a lot more continuous, a lot more kind of less varied around this. So what I'm doing is, when I sprinkle into a volume, I know where I've sprinkled all my points, and that's what I'm plotting on this y-axis. And then I can take the causal set prediction for two of them on this axis and see how they compare to them. The red line is just like x, f of x equals x. And you can see, as I was saying, this volume proper time struggles for really small tau, because the volume proper time, because we use a Poisson distribution, we basically say there is a smallest volume whereby there should only be one point in that volume. And inevitably, when I do random sprinkling, I'm going to sprinkle 2 points into that volume. And those are like these points down here. And the length of the longest chain is fine with that because it knows there are multiple points in that volume, but the volume proper time does not. And that's why it can't do the little region. And that led to, so this is just the bin values, that led to a little, I think that is what has led to it doing worse. Okay, so let's get on to some of the plots. So this is the same as before. I'm plotting the 2-point function for both the continuum, which is the red line, and the causal set, which is the blue line. And then we're trying to figure out, okay, which of the alpha vacua doesn't match. Now the answer is this kind of seems to depend on the mass of the particle, which is really annoying. But that's because in De Sitter, that 2-point function, that messy 2-point function I wrote down, kind of has two classes of solutions which depend on the mass. Above this critical mass, we find that this it is actually the alpha equals 0 case that looks very similar to the SJ vacuum. But below it, it does not seem to match any of the alpha vacua. So this is the alpha equals 0. It seems that some other alpha vacua could match for these time-like corrected points, but for space-like connected points, the 2-point function does not seem to match any of them. So it is kind of unclear. I still need to work a little bit more on figuring out what the actual consequences of this are, but that's basically what it looks like. And yes, I think that's all. Thank you.
Question?
The one behind you, John.
Oh, yeah. Shit. When you're saying, like, for proper time to take the longest chain,
yes,
is there some reason that the longest chain is closer to the mid? Like, could it not be that you have a very zigzaggy path that follows sort of these null lines around instead of being a straight line or a closer approximation to a straight line?
My understanding is basically of what I tried to explain is that if you were to zigzag around, there's not that, basically this picture I drew here. If I zigzag close to the light cone, there's not, like, there are maybe more points here because the causal set is kind of going to look random. But if I want to eventually end up here, I can't access these points. I need to stay in this diamond. But if I go in the middle, I can't maybe do what you said. I can go in the middle, but if I want to stay kind of straight, I have to zigzag a lot. And if I zigzag a lot, I'm hitting a lot of points. I'm making my chain longer and longer.
Okay.
So
yeah,
basically, I think that one that follows the middle and zigzags a lot is basically doing what I said. It is becoming the longest, if that makes sense.
Yeah. Thank you.
All right.
All right. Let's thank Thomas again.
Thank you.
I press this button, it's green. Does it matter? Did anyone pick these up?
Okay, the next speaker is Joshua Jones, and he will tell us about entanglement entropy in space-time and a signature of discreteness. Go ahead.
Right, thank you all for coming. Yeah, so I'm going to be talking about entanglement entropy in space-time, signature of discreteness, and it was actually based off some work that I did with Yasaman, who was over there and was just here. And based on this archive number here. So first I'm going to talk a little bit about relativistic entanglement entropy. I mean, you've all heard a lot about it already, but I didn't know exactly what everyone was going to say. Afterwards, I'm going to talk about an approach to calculating entanglement entropy on the causal set and in space-time volumes in general. After that, I'm going to go through an example on the causal set, and I'm just going to finish up with a little bit of outlook. Right. So, as I'm sure you are now all very aware, entanglement is one of the classic features of quantum mechanics, and it has its origin in the non-commutativity of the variables of the algebra. And entanglement can be detected by entanglement entropy, sometimes. And it is thus found myriad usage in non-relativistic quantum mechanics. This is ranging from the study of phase transitions, where it's used to probe locality and criticality. It's used in metrology. It's used to study topological order. It's used to study thermalization. And of course, it's used all over the place in the study of quantum information and quantum computing. When we turn to a relativistic setting, and this is relativistic quantum information, entanglement entropy is used maybe slightly differently, where it's largely used as a structure that not only probes, but builds fundamental physics. It's found a very natural place in black hole entropy, that is the Bekenstein-Hawking entropy, and other horizon entropies more generally. And it's also plays a key part in understanding the related information paradox. It's found a place in energy conditions, where it's used in the quantum null energy condition, and it is the reason why entropic gravity is called entropic. It's more broadly connected to the emergence of space-time, and whether it be through holography or also entropic gravity or other things like ER is equal to EPR. So, I'm sure you're getting sick of this equation, but entropy is given by the negative trace of rho log rho, where rho is the density matrix of some state. But before von Neumann came along and before Shannon, there was Clausius, who did classical thermodynamics, and entropy is, of course, very connected to thermodynamics. And from classical thermodynamic arguments, we actually know that black holes have an entropy that is proportional to a quarter of their horizon area. This is the famous Bekenstein-Hawking entropy. This is somewhat unlike more familiar thermodynamic entropies, which typically scale as a volume, because normally the amount of information you can store in something, or whatever you store it on, it's the volume of that thing. In fact, now it's known that all horizons have an entropy, and they all follow the same area law, where you have a quarter of the horizon area. So there have been countless proposals for the identity of the microstates that are responsible for the Bekenstein-Hawking entropy, but also more generally horizon entropy. But often they lack the generality to be applied to all horizons in the same way. And this has led to entanglement entropy taking its place as the leading candidate for the source of horizon entropy. So if we just go over how one actually calculates entanglement entropy, and we saw this earlier in Charles's talk, but I'm going to go over it again. So what we'll do is we'll start with a pure state, which has some density matrix, and it's pure just because it's got zero entropy. And it's in some tensor product Hilbert space, that's where it lives. And what we can do is we can think about removing, so physically occluding some degrees of freedom. So if we think of, we have some region like this, and some degrees of freedom that live in A and live in B, and the A ones are in the HA Hilbert space, the B ones in their HB Hilbert space, then if the ones in B are hidden behind some kind of horizon, then someone who is stuck in A only has access to the Hilbert space without the B degrees of freedom. And so they would have a density matrix or a reduced density matrix that corresponds to tracing out the Hilbert space B from the full density matrix overall. Then entangled state, when the von Neumann entropy of the reduced density matrix is calculated, has a non-zero entropy. And this non-zero entanglement entropy is essentially the statement that the combined state can't be factorized as a tensor product state such that it is entangled, so it's not localizable to subsystems. You can't split it into two different descriptions, one in A and one in B. They have to be described together. When we pass to quantum field theory, generically the quantum field is an operator valued distribution, but for our purposes, distribution kernels will suffice. When one calculates the entanglement entropy of a vacuum state in quantum field theory, one can go about it much the same way, and one finds an area law scaling. The problem is that the coefficient of the area law is infinity, so it's unfortunate. You can somewhat think of this as if you were to do the Schmidt decomposition of a quantum field vacuum state, much as you would do in ordinary quantum mechanics, into localized states, you would find that you split up your quantum field vacuum state into some tensor products of states that live in A and states that live in B, and you generically find that you need an infinite number of these tensor product states, and they all come with this coefficient, the square root of lambda. And if you go ahead and form the density matrix out of this state, when written like this, and you think about tracing out, let's say, B, and calculating the entropy, you'll find that what you're calculating is the sum over lambda log lambda, and generically this thing does not converge. So the nature of this divergence is an ultraviolet divergence. You can see that because we're having states of infinitely high frequency all contribute. But any sufficiently well-motivated regularization will return for you an area law. So you'll get the S is proportional to area that we were inspired by from the area law scaling of black holes and other cosmological horizons. Ordinarily, one thinks about regularizing by imposing a length cutoff on the Cauchy surface. But what that means is that when one calculates entropy, one finds that it is frame dependent. And this is directly inherited from the way that we regularized. If one thinks about nature, in nature, quantum gravity should be supplying the regularization. And if one believes that quantum gravity is covariant, then what one needs is a space-time volume means based of calculating the entropy such that you can actually apply a covariant regularization. So Yasaman and I gave such a means of calculating entropy. And so this is for quasi-free states. So you can think of these as free states or those that have a Wick's rule that is the same as free states. So if we start with the case of bosons, what you need to do is consider the two natural space-time bilinears. That would be the two-point function of the state and the commutator of the state. What one does is then one promotes them to operators just with the L2 inner product over the space-time region of interest. And what one writes this generalized eigenvalue problem where we have an eigenvalue lambda. And you solve this on the space of test functions. So that is L2 normalizable functions with compact supports over the space-time region. So you solve this generalized eigenvalue problem, get the eigenvalues, and you just plug them into the sum of lambda learn the absolute value of lambda. If one looks at fermions, things are much the same, except to get the to account for the spin statistics, one needs to have the anticommutator instead, and the sum is slightly different, where the sum is now minus the sum of lambda log lambda with no absolute value. So given that this formula is written in spacetime, we can actually go about performing calculations of entanglement entropy in spacetime regions or on the causal set. So for the actual calculation to be done, you still need to specify a few choices for an actual calculation. So you need to choose the regions that you're interested in, you need to choose the state that you're interested in, and you need to choose how you want to regularize. Each of these choices is actually a physical choice. The choice of region and state are easy to see why they're physical, but also the regularization is a physical choice, as it's your manifestation of quantum gravity. So I'm going to now just cover an example, just to see how everything works. So in this example, we're going to do the simplest entanglement entropy calculation known, or that I know, which is Rindler in 2 dimensions. And this would ordinarily be Rindler space, which looks like this. It's infinite. But we're going to take a massless field, so we impose an infrared cutoff because there is no massless Minkowski vacuum in 2 dimensions. We now need to choose a state. In spacetimes with symmetries, there can exist a preferred state of some kind, being the Minkowski vacuum, Rindler vacuum, Bunch-Davies vacuum, and in spacetime without symmetries, we can use the Sorkin-Johnston vacuum, which hopefully you all still remember from Thomas's talk. This is also happens to be the canonically chosen vacuum in the causal set, so we're going to use it here. And another handy thing, which you know already from Thomas's talk, is that it can be constructed causal set natively in flat spacetimes. It's also known to agree with the canonical vacuum for static spacetimes, and so it would have been Minkowski in this case if we hadn't put an infrared cutoff in. So this was my slide for the Sorkin-Johnston vacuum. I didn't know what Thomas was going to say. But if I am going to recap what I think you need to know for this, what you do is you start with the retarded green function, which you have existence and uniqueness for on a globally hyperbolic spacetime. which also is known causal set natively in flat spacetimes. And we can use the Perel's relation, which applies for quasi-free theories, to essentially write the commutator, spacetime commutator, as this combination of retarded minus advanced green functions. This factor of I is different from Thomas's because he put that on the definition of the green function. And I'm just going to call the commutator I delta, delta being the difference between the retarded and the advanced. The Sorkin-Johnson state is then defined via taking the positive part of I delta, where positivity is with respect to the L2 inner product over the space-time region of interest. And this is what gives what is called the Sorkin-Johnson state. Now it's time to turn to regularization, where I am going to use the causal set. So a regularization is a direct choice of the physical manifestation of a theory of quantum gravity. And we are going to use causal set theory to perform this regularization. Hopefully, you have all not forgotten Liam's talk, so I don't need to tell you anymore. However, if I'm going to, again, summarize what I think is important for this calculation, in causal set theory, one essentially replaces the space-time manifold with a directed acyclic graph. You will notice that I am doing exactly what Liam said not to do, where I'm getting the ontology the wrong way around. So I'm thinking of a manifold, and I'm replacing it with a causal set. If I do that, what you can think of is these elements being fundamental units of space-time, and this causal precedence relation being inherited directly from the manifold used to create it. If I want to recover the continuum manifold, you can just use the counting measure on the set, on the partially ordered set, whilst preserving the order relation. So this is also something Liam mentioned. This makes sense because of some theorems by Hawking, King, McCarthy, and also Malamant.
Can I just ask a question about causal set theory?
Mm-hmm.
How are the points like causally related on based on their nearest neighbor sort of thing? Is that like their nearest causal neighbor obviously inherits
So
from the
it really is, so this thing, so this diagram here is a Hasse diagram. So this point is related to, well, this point, this point precedes this point, but it also precedes this point, right? But I've just...
the point beside it. How do you determine whether or not it's causally related with that point or over that point?
This one or this one?
No, the one just now.
This one?
Yeah.
So...
Is it outside of its light column?
So I'm doing the ontology wrong. So what you would think of is you would start with a manifold. You would essentially assign points into the manifold according to the volume measure of the manifold. And then because your points are in the manifold, you can essentially see whether they're causally related or not, right? So you would think of this thing having a light cone that looks like this, where this is not inside, yeah. So this means that for our problem, what we have is the Sorkin-Johnson state on a causal set that looks like this, where we have big diamonds, and we split it into 4 small diamonds. So before I go on to what was calculated, I should talk about what we might expect. So I started this talk by saying that we care about entanglement entropy because it scales as an area law, and Beckstein-Hawking entropy and horizon entropy is an area law. Well, actually, in 2 dimensions, it's not an area law, like many area laws. It's a logarithm. So if we have a setup and we impose an ultraviolet and infrared cutoff, just like we have here, the infrared being the size of the big diamond, the ultraviolet being the causal set itself. We can expect a universal scaling law, essentially from conformal field theory, where you find that the entropy scales as 1/6 the logarithm of the infrared scale divided by the ultraviolet scale. And then one also finds a non-universal constant here. Because we expect the universal part of our entanglement entropy that we calculate to match that which would be calculated on this Cauchy surface, for which our large diamond and small diamond are the causal, well, are the domain of dependence of, we would expect that we calculate an entropy that matches this one. So to go over the procedure again, what we do is we start with the Sorkin-Johnston two-point function, which you get via L2 positivity on the causal propagator. You then restrict the two-point function and the space-time commutator, so I times the causal propagator, from the big diamond into the small diamond. And then you use this formula, where here this M would be the small diamond, to calculate the entropy. So on the causal set, our space-time bilinears are going to be matrices, because we have finite number of points instead of a manifold. So we can essentially just solve this numerically. We can solve the generalized eigenvalue problem numerically, and then insert the eigenvalues lambda into our entropy formula, which is the same as above, the sum of lambda ln absolute value of lambda. If we go ahead and do that, this is what we get, where I have plotted entropy on the y-axis, and on the x-axis I have essentially plotted a substitute for the infrared length divided by the ultraviolet length, which in the causal set can be seen as the square root, because it's two-dimensional, of the number of elements in the diamond. When we actually go ahead and fit to this, so it looks like a logarithm, yes, so we fit a logarithm of the square root of the number of elements with the coefficient b and just some constant c. We find that b is 0.198 plus or minus 0.014, which is significantly different from the 1/6 that we expected. And we take this to be a signature of discreteness, essentially because a very similar calculation was done using a different type of regularization, which doesn't involve discreteness in the same way, but it involves a truncation of the spectrum that we expanded. And that one matched the 1/6 incredibly well. So if I now finish with some outlook, I'll say that not only does this calculation tell us about entanglement entropy, but it also tells us about the nature of quantum field theory on the causal set. And a natural question that arises would be, well, the immediate question is, how can we actually understand this difference? Where is it coming from? How is it actually encoded? So everything in this calculation flowed out of the causal propagator, which is the difference between the retarded and advanced green functions. You remember I got the state via L2 positivity on it, and the entropy only involves the state, the causal set, and this delta, which we use to make the state. So how is this difference actually encoded in the delta? And then also some other questions come to mind as well, such as whether a similar difference inherited from the causal set will show up in higher dimensional treatments, and whether it will be as stark. You can think that perhaps in the two-dimensional case, there's a relatively big difference because there actually isn't an area law. But perhaps this difference will be subleading in higher dimensions. And of course, I showed you a formula for the bosonic case, but I also showed you a formula for the fermionic case. And a fermionic calculation actually hasn't been done, so I don't know what will be found in a fermionic calculation. And finally, of course, the non-universal constant here, how can we study it, and what actually does it mean? So with that, I will leave you with a QR code to the paper, and I look forward to your questions.
Thanks, Josh. The way that I see the area law scalings and things like this is as a direct consequence of the Hadamard condition. It's a direct consequence of this UV behavior of the short scale of the correlations, right? Mm-hmm. So it's interesting that, I mean, you started the talk by motivating with all of these applications of area laws and how fundamental they are, but at the same time, it doesn't seem to be a criteria that can be implemented at the fundamental level in causal set theory, right? But this is not a question, it's just a comment. Okay. So let me ask you a question, right? So the question, can you go back to your plot when you show the best fit? My question is basically, so if you only try to fit the portion of the curve, like if you neglect all values for sufficiently small n, do you still get a B that is this different from the expected value? Because I would expect to find more differences when you have like a smaller number of points, but then asymptotically still, maybe you find something, because if I look at this plot, like it looks like for sufficiently high n, like these are matching very well, right? So it's just, I just wonder whether this best fit isn't incorporating like...
This best fit is this one.
The blue curve there is the best fit. It's not the actual S, like the actual one with the 0.167.
It's 0.198.
Okay, and what happens with this best fit if you just like if you neglect like the lower values of n? Do you still find a B that is this different?
It's pretty much the same. So actually, this plot it's weighted by 1 over the variance. So it cares much more about these large points.
Okay, so it's a reliable like asymptotic limit.
It's really the large points that give you. As you can see, you know, the uncertainty over here is like. You don't have control, right? It's really the large points that give you an uncertainty that's actually small enough to say, oh, this is different. Yeah.
And then now going back to my comments, so given that it's like it's all about the short scale behavior of the correlations and all this, does the SJ prescription satisfy the Hadamard condition in this specific spacetime with cutoff IR and UV cutoff that you picked, or not? Do you know that? Because if it does, then there should be no discrepancy whatsoever, right? In the really long short scale behavior.
Well, so, I mean, the first thing would be that, you know, nothing on the causal set can really strictly satisfy the Hadamard condition, right? But
I mean, the continuum limit.
You're asking about the continuum state, yeah. So. I think it does, yeah. Okay, well, okay, it does away from the boundary, right? Where, yeah, it diverges on the boundary. So yeah, it satisfies it everywhere but the boundary. Yeah. Okay. More questions?
For the entropy formula that you gave, I was just wondering what the motivation was for that particular eigenvalue problem. Like,
well, so here's the thing is, so this is for a quasi-free state, okay? So, and when I say quasi-free, just think of a free state. A free state has essentially all of its information contained in its 2-point function, because the higher point functions you can get just writing contractions with a 2-point function. And so if all the information is contained in the 2-point function here, well, Well, all you need is a way of extracting the information in a conducive way for it to be repackaged into entropy. And so if you think of the mode expansion of this and the mode expansion of this, you'll see that essentially combinations are coming out of, you would say, let's say positive and negative frequency basis functions. But those are exactly the things that you have coefficients in front of that you would use to calculate entropy. It happens to be that these things come out in very handy combinations, such that you only need to sum them like this. So I should say that in the bosonic case, these things are not. You might think, oh, this looks sort of like probabilities. In the bosonic case, these are not probabilities. So for each mode, you have 2 eigenvalues. But it happens to be that they're packaged up in a way that algebraically, if you just will subtract one from the other, you will get the entropy of a mode. So I guess the word that people sometimes use is maybe scheme dependent or something like that, where you would think of, let's say if I wanted to put a lattice on here and then start thinking about taking the limit, this thing will have some memory of what your lattice was. And it depends on exactly how you do the calculation, how you decide to regularize. Yeah.
Thank you.
There are no further questions for the moment. Let's thank Josh again. Matter?
That's fine.
I just need a minute to connect and stuff.
Do you want the wooden stick or the high-tech stick? Our next speaker will be Yasaman Yazdi, who is going to be talking about the causal propagator and its spectral density.
Thank you. As mentioned, I'm going to talk about the causal propagator that you've been introduced to already in the previous 2 talks, and which is one of the most important quantities in both classical and quantum field theory. And I'm specifically going to talk about its spectral density, as mentioned. So this is based on recent work with Josh and with Raphael Sorkin, and the details can be found in this paper. There are three broad topics that the subject of my talk is connected to. These three topics are putting quantum field theory into a more explicitly space-time or covariant or frame-independent framework, doing Lorentzian spectral geometry, and causal set theory. So you've heard a little bit about each of these three topics. I'm just going to review some facts about them again. It is expected that the UV divergences of quantum fields are going to be regulated in any generic curved space-time. And we also expect this regulation to be done in a frame-independent way, because classical gravity, as well as numerous experiments and observations, tell us that generically in any space-time, there are no preferred frames. And this is upheld by most quantum gravity approaches as well. Now, in order to be able to UV regulate in a frame-independent way, our quantum field and its degrees of freedom need to live in space-time, meaning that they need to be described in terms of quantities or objects that have support in space-time, rather than space, which is where many other conventional formulations put them. We already heard a couple of examples of how this can be done. This was the Sorkin-Johnston prescription for defining a state, and the space-time formulation of entropy or entanglement entropy. And we also saw that these formulations used spectral methods, meaning that we had to work with the eigenvalues and eigenfunctions of operators to describe the physics. So this brings the connection to spectral geometry, which is traditionally studied on Riemannian manifolds. But here we are doing Lorentzian spectral geometry, which is much less studied, much more difficult, and much less understood. And finally, the connection to causal set theory comes because causal sets are intrinsically Lorentzian and spatiotemporal in nature. So we have no choice but to describe things like quantum fields on them in a space-time or global manner, which is the better way of doing things anyway. And the causal set also provides us with a covariant UV regulation of those quantum fields. And it also turns out that some of the difficulties of Lorentzian spectral geometry can be circumvented by working with causal sets, because a lot of the computations of the spectra become numerically a lot easier with causal sets, making these problems more feasible, as we'll see. So this is the main context of the talk, these three topics and the interplay between them, and I'll say more about that throughout the talk. And at the heart of all this is the causal propagator, or the Pauli-Jordan function that has appeared in the previous talks. It's usually denoted by delta, and classically it's the difference between the retarded and advanced green function, where the retarded green function is this solution to the inhomogeneous Klein-Gordon equation. I'm just going to consider a free scalar field theory. So it is only non-zero if the second argument causally precedes the first argument. The advanced green function is just the transpose of that, so it's only non-zero if the second argument is in the future of the first argument. As an operator, the image of delta is equal to the kernel of the field equation. So it has all the important information of the field theory. And if we have delta, we don't actually need the field equation, because, for example, the eigenfunctions of delta with non-zero eigenvalues give us the full information of the solution space of the field equation, which is the important information that we're interested in. And finally, in the quantum theory, I times delta is the commutator of the field. This is also sometimes called the Peierls bracket, And in all of these expressions, x and x prime are points in space-time. Here are some properties of I delta. It's Hermitian, it's pure imaginary, it's antisymmetric, and its non-zero eigenvalues come in plus or minus pairs. The eigenvalues have dimensions of length square, and at least in compact space-times, they are bounded above. Given how important I delta and its eigenvalues and eigenfunctions are in space-time formulations of quantum field theory, a general question that we're interested in is, can we gain further insights about the eigenvalues and eigenfunctions of I delta in a general, compact, and globally hyperbolic space-time? The claim is yes, and I'm going to state a conjecture for the form of the eigenvalues and eigenfunctions of I delta in an asymptotic limit. By asymptotic, I mean ultraviolet or small eigenvalue limit. But before doing that, I'm just going to review an example where the eigenvalues and eigenfunctions of I delta are very well understood both analytically and numerically. So the example will be that of a massless scalar field in a causal diamond in 1+1 dimensional Minkowski spacetime. So this is the setup. We have our causal diamond here with side length 2L. It's useful to work in light cone coordinates defined here. So t plus or minus x divided by root 2. Delta in these coordinates looks like this. It's just a combination of two step functions. So it takes values of either 1/2 or -1/2 or 0, depending on the causal relations of the pair of arguments that it has. And this is the eigenvalue equation that we're interested in solving. There are two families of solutions to this eigenvalue equation. This fk and gk family of eigenfunctions. So they are both linear combinations of plane waves at the same wave number k. This one has an extra constant term in it. And for the f family of eigenfunctions, the k's look like this. They're just an integer n times pi over L, where n can be either positive or negative. And the k's for this G family of eigenfunctions, they're a little more complicated. They're the solution to this transcendental equation, tan KL equals 2KL. For the non-zero ones, for k not equal to 0. And the eigenvalues for both sets of these eigenfunctions go as L over k. So for the respective k's that satisfy these two conditions. Yes?
So using the same symbol k, slightly different for a lot of different things.
So you mean between the F and G family?
Yeah.
I
mean, you can do it. It's just rather confusing.
Sure. I mean, they're, I suppose, yeah. They're both wave numbers, but yeah, there are wave numbers for both the F family and G family, yeah.
I think it makes sense, Charlie. It's like k equals this or it equals that.
It makes sense logically, but I couldn't do it. But anyway.
Okay.
Sorry about that.
Are you imposing boundary conditions around the diamond?
No.
So why do you get, where do you get this discreteness for the k?
So, I mean, so this just comes from the fact that it's a compact region. This is just how it comes out to be. So it's bounded above, and then it accumulates around 0.
With no boundary conditions in that?
With no boundary conditions. Well, other than the fact that the region is defined to only be this compact region, so that.
You can't have a continuous set of
Right.
put boundary conditions to obtain your eigenvalues.
Otherwise, you wouldn't be able to have things like S1 or S2 or S3.
But there's no boundary there. But there's no boundary in that case. Effectively, your boundary conditions for your decision, right?
You don't need a boundary. If you have a boundary, you've got to give boundary conditions. There's no boundary.
There's a boundary.
There's a boundary.
Well,
Maybe.
It's okay across
We
the
should discuss this.
Later.
in the discussion session. Okay. Okay, so the eigenvalues for both sets go as L over K for K, the respective Ks of these two families of eigenfunctions. And asymptotically, so in the small eigenvalue and UV limit, the K solutions to this transcendental equation actually approach the same expression as for the Ks for this other family. So we can write down the explicit expression for both sets of families of the eigenvalues in the asymptotic UV limit. They go as L square over n pi. And this is another reminder of the fact that these eigenvalues have length dimensions, length squared. We can go over the same exact example now on a causal set background. So this is the setup. This is the causal set version of the causal diamond shown as an embedding in the original Minkowski diamond. The points are randomly and uniformly distributed. This is characteristic of a Poisson sprinkling, which is defined as having this distribution of elements such that the probability to have n elements in a region with volume, space-time volume V goes as this expression, rho v to the power n over n factorial times exponential of minus rho v, where rho is a constant density parameter that sets the discreteness scale. Our I delta, or causal propagator times I, has this simple expression. We saw it in the earlier talks. It's just I times 1/2 the transpose of the causal matrix minus the causal matrix, where the causal matrix is a matrix of ones and zeros, depending on whether or not the elements are causally related. So this is analogous to the combination of step functions that we have in the continuum problem. This is the direct analog of that in the causal set in terms of an object that is very intrinsic to the causal set, which is this causal matrix. Now, in order to compare the eigenvalues of this discrete causal set I delta with those of the continuum, we need to dimensionally divide by a factor of rho, which is this discreteness parameter. And here is a plot in the blue dots of the largest 3,000 positive eigenvalues of the causal set I delta, shown on a log-log plot. And in red is shown this 2L square over n pi, which was the expected asymptotic scaling that we found from the continuum version of the problem. So we see that there's good agreement between the causal set eigenvalues and the expected asymptotic scaling of the eigenvalues from the analytic problem. Just for comparison, the green and orange dashed lines are just two other scalings, which are not a good fit.
So what is this agreeing with? I don't understand. The green and red lines we can ignore.
Yes.
So what am I comparing with what?
So the blue are the eigenvalues that come from diagonalizing this.
Yeah.
And the red is this from the continuum problem. This is just an exercise to show that the causal set and continuum problem are in agreement.
Okay. So this one's a minor, the other is a set of points.
Yes. So the example that I just went over is one of the very few examples where we know the eigenvalues and eigenfunctions of I delta explicitly and analytically. But now I'm going to state the conjecture that is a conjecture for the more general kind of insight that we're hoping to have on I delta. And it's a conjecture for the form of its eigenvalues and eigenfunctions, again, in the asymptotic limit in the ultraviolet limit or small eigenvalue limit. So the conjecture is as follows. Asymptotically, each eigenfunction of I delta is associated with a null geodesic with momentum. We can then identify the spectral measure of I delta with the measure on the phase space of these null geodesics with momentum, which is the Liouville measure. So in other words, we have rho tilde lambda d lambda is asymptotically to be identified with, this is the Liouville measure, so dx to the d minus 1, dk to the d minus 1 over 2 pi to the d minus 1, where rho tilde is this spectral density. Each eigenvalue, again asymptotically, has the form 1/2 d alpha k integrated over the geodesic, where alpha k is the affine parameter that gives the momentum as the tangent vector of the geodesic. So in other words, if we choose coordinates, the raised momentum k mu is equal to dx mu d alpha k, where mu is not to be summed over. So this is a lot to take in. I'm now going to talk about what some of this means and how we can apply this to actually compute some spectral densities and get more handle on what the eigenvalues of I delta look like in more general settings that we before did not have a handle on. Yes?
Yes, can you tell me again, my intuition is getting a bit mixed up. Why is it that we're interested in small lambda?
Because that's the ultraviolet limit. So it's bounded above.
Okay.
Yeah. Okay. So we can use this conjecture to compute some spectral densities for I delta, and we can do that in the following way. Restricting ourselves to just the positive eigenvalues of I delta, because remember the eigenvalues come in plus and minus pairs, and the pairs are identical, so it suffices to look at just one sign. We're going to look at the positive ones. We can define this counting function n that counts the volumes of greater than some specified value of our eigenvalue. We can then differentiate this to get our spectral density. So we're going to get a delta function. And here I've just substituted the explicit form of the map of the eigenvalue in terms of the affine parameter. And then to actually compute this in a particular setting, in a particular compact space-time, we would choose a Cauchy surface sigma that each geodesic intersects once, and we would choose coordinates, and we would get an expression that more explicitly looks like this. So here I've just substituted in the Liouville measure explicitly, and in coordinates our d alpha k looks like this. And we would just integrate this over our chosen Cauchy surface sigma. I'm going to show some examples of this. So if we apply this to the 2D diamond example that I just went over, we would get an answer that is in agreement with the known example. So I'm going to instead show you an example in the 3- and 4-dimensional causal diamond, which were before not known. Very quickly. So here is the 3D diamond example application of this spectral density. This top expression is just the general expression I had on the previous slide. We can choose one component to evaluate this. I'm going to choose the time component. So in 3 dimensions, we're going to have an expression like this to compute. We evaluate this on the 3D causal diamond. The answer that comes out looks like this. So dn d lambda is equal to 4 L square over 15 lambda cubed, where L again is the half side length of now our three-dimensional diamond. And we can turn this into an expression for the eigenvalue lambda itself. So lambda asymptotically turns out to have this scaling. So there's a prefactor square root 2 over 15 times L square, and importantly, the scaling with n is an inverse square root n scaling. So this is the expectation from the application of the conjecture. And as I said, we don't have analytic answers for this and many other cases, but we can go ahead and compute this in the causal set and compare the answer we get there with this expected scaling. So I will maybe not go over the details, but this is just the picture of a 3D version of, or a 3D causal set version of the causal diamond. In the continuum, the retarded green function for this setting scales as inverse of the proper time between two space-time points. We saw from Thomas's talk how we have some proper time estimates in the causal set. We can use that to get the analog of this kind of expression in the causal set. Once we have the retarded green function, we can get our causal propagator delta as the antisymmetric part of that. So doing that and then going ahead with the diagonalization, here is the answer that we get. So again, in blue dots are the causal set eigenvalues of the three-dimensional delta in this causal diamond on a log-log scale, or the largest 5,000 of them. In red is the expected asymptotic scaling that we had from the conjecture calculation. And we can see that it's in roughly good agreement with the numerical answer. And again, there's just two comparison alternative scalings to show it is not those.
It's not in rough agreement, it's very good agreement.
In very good agreement. Glad you think so. So now this is just the four-dimensional version of the same calculation. This is, again, the general expression. This is applied to our four-dimensional diamond. Again, we're going to use the time component. The answer that we get is the spectral density goes as L to the power 6 over 6 pi over 6 pi lambda to the power 4. Turning that into a scaling expression for the eigenvalue lambda, we get that in, I should say, 4 dimensions. In 4 dimensions, in the asymptotic limit, lambda scales as inverse cube root of n with a prefactor that is L square over 2 times 4 over 9 pi to the power 1/3. Again, we can compare this with the causal set calculation. The retarded green function in 4 dimensions is a delta function on the light cone. The analog of delta function on the light cone is the link matrix, because a link between elements on a causal set is the closest thing to a light-like relation. So having the analog of the green function, we have the analog of the delta in the causal set. Again, we do the diagonalization. The blue dots here, the red line is the expectation from the conjecture calculation. And we can see, again, this time maybe it's fair to say they are in rough agreement. And again, two alternative closest or close scalings that it is not in agreement with. So in both of these new examples that we have from the conjecture, it seems to be holding up, at least when we compare it to the causal set numbers that we are getting. And just to summarize, so there has been a lot of ongoing work on putting quantum field theory in a more space-time, explicitly space-time form. And this is both in the continuum and in causal set theory. And the latest developments have had some very interesting results in the context of Lorentzian spectral geometry. So the conjecture that I showed you is the Lorentzian analog of Weil's asymptotic law in Riemannian spectral geometry, which is one of the most important results there. So just to mention what that is. So Weil's law describes the asymptotic density of the eigenvalues of the Laplacian in a Riemannian manifold. And there, the leading asymptotic shape of these eigenvalues is known to be of this form. So it's a known power law, and the prefactors are also understood in terms of geometric quantities like the volume of the manifold. And so here we have something that's very analogous to that, but in the Lorentzian context. So it opens a lot of possibilities for further exploration, both in the context of Lorentzian spectral geometry and the more physical applications of it in causal sets and quantum field theory. So with that, I'll end. Thank you.
Well, we have a general discussion session now, so.
Oh, do we? Oh, right. Do I need that microphone thing? Yeah. Oh, so that it goes on YouTube. Hello, YouTube. So, yeah, I'm very pleased to see that you had the words of Weil's asymptotic law, because I was going to ask you about it. But, this applies to a positive dimensional elliptic operator. It doesn't have to be the Laplacian. You just have to make an adjustment to the number 2. But it also applies to any pseudo-differential operator, which allows you to go into negative order and non-integral order, in irrational order. And what you've really got is an integral operator, so it's a negative pseudo-differential operator, an operator of negative order. And that'll immediately give you the thing that you have. The thing that I don't understand, and yes, there's a good place you can look for. You know that one way of studying these by complex variable theory, these meaning Weil's law, is to use the zeta function, right? So you take the eigenvalues, you consider sum of 1 over lambda to the s. You know that, right? So the singularities of that give you a lot of information. You can do that in this case as well, and you will get a couple of interesting things which are kind of related to even von Neumann theory. There's a thing called the Dixmier trace. I don't know if you've come across it, but if you look at that, you can study it with a zeta function-like object. You'll find an account of this in Cohn's book on non-commutative geometry. And there's a necessity, if there is a pole, which there is in these cases, to find out what the residue is. Is it non-zero, and what it is? And there's a thing called the Wodzycki residue, which tells you what's going on there. But all of that would seem to be generic. You would predict this even if you weren't doing physics, because this has nothing to do with causal set theory. And the thing I don't understand, but that's because I just don't understand it, is I'm not so easy able to see the intuition of why this would be particularly Lorentzian. I would have thought this would be much more to do with the fact that the manifold is compact and that the operator has a negative order and it's pseudo-differential. Where does the Lorentzian come in this?
Kernels of the operator.
What?
They're huge kernels.
Yeah, but that doesn't matter. What's left? What I say applies to what's left. It's just an operator. You take the image of this I delta, whatever it is.
But it's an operator on a Lorentzian manifold. It's an operator on a Lorentzian manifold.
Who cares? It's still an operator.
For gravitational physics, we care. But
yeah, we care. The eigenvalues. If the eigenvalue was 3 instead of 105, that would have a physical importance for us. But from the point of view of mathematics, it's an operator, and you just need things like: is it bounded below? Is it positive? And then the machine works. Well, the physics of it is a different thing, but you do actually get the predictions about the asymptotic growth or decrease.
Weil's law relies on it being elliptic.
Weil's law relies on it being elliptic differential, but when you've projected out the image, from the thing, I think you must have an elliptic operator. That's why I asked the question, where does the Lorentzian come in? See, I could take a hyperbolic operator and I could kill part of it and I'd leave elliptic part. See, I know it comes in there. I know what you're going to do. You're going to show me that slide.
Okay. Besides this, I mean, I don't know what to say.
No. No, it's non-elliptic, but what about image of delta, right? Is that non-elliptic or elliptic?
No.
So it's hyperbolic?
Yes, it's hyperbolic.
People are saying yes.
It's a non-local object.
Yeah, it is, but you can still talk about it. The elliptic operators of non-integral order are all integrals of some kind, so that's nothing to do with it. But what is to do with it is elliptic or hyperbolic.
I don't think so.
Okay, but do you know?
Well, there are many things that I do I know. Probably.
Because you see, if it's hyperbolic rather than elliptic, then it has a singular set, and the support of that singular set is big. You know, it's got a positive dimension. And do you see that? You do?
Get a lot of zeros. You get a lot of zeros, right?
No, not zeros. Just infinities, all kinds of stuff, where the operator doesn't behave nicely. Think of the classical wave equation.
So you have, so he's a Fourier integral operator, but he has, you know, he's hyperbolic in the sense that he propagates singularities, right? He doesn't kill singularities, right? So he propagates singularities along the bi-characteristics of your Lorentzian manifold, right? So that would make me inclined to say that he's hyperbolic.
Yeah, I guess I don't understand that properly, but that's interesting because what that means is, and remember, you know, I could be talking rubbish, that if I ignore that, which I'm sure I shouldn't, I'm still getting a result which I would have expected if there was no hyperbolicity anywhere. So it doesn't seem to matter.
Well, the scaling comes out to be very, very different, right? If you were to look
You
at
looked away then, so I didn't hear. I'm getting rather old, so I don't hear everything.
If you look at Bell's law and you compare it to the scaling that you get here, it's very different. Let's say dimension-dependent scaling, or even the fact that if you look at Bell's law, the first term is a volume term, right?
Yes.
It's not the case here.
What is the first term then? The volume, you see, is not well defined in the Germanian sense in this causal set program.
No. I'm doing it.
Talking about a finite causal set.
I'm talking about the continuum here.
You're talking about the continuum. Yeah.
Can you show us your conjecture? So.
Yeah. It won't come out to be the volume. Well, it does in 1+1, but otherwise.
Vice formula comes out with the volume in every
I know.
dimension, so I'm not quite sure what you're saying there.
Well, I'm saying it's different from Basel. I'm saying, you know, if this were Basel, it wouldn't be that. It would be very interesting, right?
I don't understand what you mean. I understood
so
the
I have a hyperbolic operator.
Yeah.
And I have the leading asymptotic scaling.
Right.
This is analogous to Basel.
Yeah.
It's not Basel.
Right.
Because Basel is for compact elliptic.
Yeah. Right.
So, and the scaling comes out to be quite different from that of Basel.
Okay, so if we take, you know, the power of lambda that comes in, you know, so the coefficient has got some numerical coefficients, and then it's got a geometrical bit, right, which roughly speaking in Weil's case for elliptic operators is a volume, right? Not always, so in a non-compact manifold it's not a volume. So in your case, it's what?
It's not a volume.
But what is it? It's a geometrical thing to do with the setup.
It's to do, well, it's because space and time are different, right? It's essentially space to some power, time to some other power.
Yeah, okay. So it's a geometrical object.
Yeah, and they're different.
Made from those.
Yeah.
Yeah.
Yes, exactly.
But still, the fact that they get this power law with this geometrical factor, which is Lorentzian, now I see how the Lorentzian is going to come in, is very suggestive. That the same mathematical mechanism may be underlying it. And
oh yeah, I'm sure you can. Yeah. I mean, you can write the equivalent, say like P kernel, right? And start.
And if the manifold is non-compact, you know you don't get even in the elliptic case of volume, you can get anything. You get logarithms and all kinds of stuff.
If the manifold is not compact, then the causal propagator is not compact as an operator.
No, it isn't. And I presume that do the causal set programs ever use an infinite number of dots or whatever.
No, but this conjecture is really strictly about the continuum.
Yeah.
In the causal set, so the conjecture has sort of at its core actually the assumption of there's a certain smoothness of space-time, right?
I don't know about that.
It has to be
You can't do that, otherwise you're not doing causal sets. I mean, if you
at
have...
some scale, the causal set looks smooth.
Well, that's different. The other thing is that time is meant to be non-compact in my real world.
Yes.
So wouldn't that require you to have an infinite number of dots or points?
An infinite number.
I
Well,
mean,
non-compact. Then the numbers coming out are going to be infinity. I'll tell you that.
The numbers coming out what?
The eigenvalues are going to be infinity.
But that's not the same either.
I mean, if I'm taking some...
I mean, if the standard space-time, without being fancy, is sort of something of the form S Cartesian plotted with R, then the R is a sort of Cauchy surface times an R. The kind of thing that Girac would write down.
It is S compact.
Yeah. Yeah, but the R isn't.
No, but it is the S compact, yes.
Well, yes. Yeah.
but when you say R is not, what is the reason for that?
The real line is not compact.
Right, but why would you choose it not to be?
13.8 billion years is pretty far to me.
Right. Exactly.
That's just a religious. Even if it doesn't stop, it's at least semi-compact. It's semi-infinite. So anyway, you don't do that. You have a finite number of points.
Yeah.
So it's compact regions of space-time.
Yeah, it's compact regions of
Yeah.
space-time.
But it's compact with boundary. Right? Because compact space-times have those time-like curves. So it's compact with...
Yeah, if it's four-dimensional, yeah, I agree.
Yeah,
yes.
globally
I was going to
hyperbolic
ask that,
compact,
but
yeah.
I thought that would be too
Yeah.
much.
But your conjecture, I think, shows very clearly the relation with Weyl's law, in that you would have written that for Weyl's law, you would have just written that d to the d. And
Yes, yeah, the dimension.
Yeah, that's true.
the
Yeah, that's a bit that
Yeah.
I didn't really notice too much, but you've got it split, as Josh pointed out to me, into space and time. Josh, you better take this back before I get
Forgot about it.
carried away.
So I guess when you write down a conjecture, there's the obvious question of asking about the status of the conjecture and prospects for proving it.
So this is 1 month old, so so yeah,
But is there a pathway to proving it?
Yeah, I think essentially probably using the same methods that Weyl's law was proved. Some reading of things are required on our part to attempt it, but I think people who are familiar with it can probably easily do it using the same methods.
How did you come up with the conjecture? Was it just through doing numerics and spotting the pattern, or was there some other way?
So I think, I mean, one of the key ingredients of the conjecture is actually the insight that this I delta operator is the relevant operator to focus on. And through our work in quantum field theory, which itself was inspired by trying to do quantum field theory in causal sets, we were already thinking about I delta a lot in this context of quantum field theory. And like I said, the methods were very spectral in nature. And by trying to understand those spectra more closely, that essentially led to these latest insights that ended up having a more broader mathematical relevance. So.
You have this kind of systematic step structure in your causal set data in the prior slide. Can you explain where that's coming from? Or especially
You mean this? I'm not sure, but I suspect it has to do with the degeneracy of the eigenvalues. So yeah, I suspect it has to do with the degeneracy.
Yeah, sure. In the standard elliptic case, if you don't know about the degeneracies, you'll get completely the wrong answer.
Mm-hmm.
So it does have to do with degeneracy.
So in the 2D case, we know there's a twofold degeneracy. In higher dimensions, we don't know. But whatever the degeneracy is, you'd expect it to show itself in this sort of step-like feature.
So I understand that at least in 1+1, it's now to me easy to see that the operator is compact and everything, like the integral operator. Because I mean it's a discontinuous function, but it's fine. Still, you're integrating it against something, and it's okay. But if you go to higher dimensions, you start having these direct deltas in your kernel of the integral, right? So is there an easy way of saying that these will be compact operators still there? In it?
Energy estimates. Do you want to elaborate? Okay.
Just the reason for it to be compact. The reason is because he's bounded. You know, he is compact, right? The space-time region, and then by energy estimates, you can see that the operators are compact.
Yeah, I agree. Okay. I agree that the delta function one's a bit trickier to see, but at least in 3 dimensions, it's a nice function still.
Yeah, if you can, yeah. You just need to be able to bound it properly, I guess. But yeah, okay. Thank you.
Does anyone have any questions that are not for Yasaman?
So should we thank Yasaman again?
Oh yeah. So, I mean, I guess now the discussion session is starting somewhat. Does anyone have any questions that aren't for Yasaman, for a different speaker?
Thanks.
All right, well.
Yeah, I had a question about this time-right geodesic, I think, was Simon. So you gave the definition. So your definition was, as you'd expect, that it's length maximizing. Is it locally length maximizing or length maximizing? Because in the continuous case, it's time-like geodesics locally maximize proper time. And what
All right, and our final speaker of the day will be Denjoe O'Connor, who is going to be telling us about counting states in gauge orthogonal invariant matrix models and possible connections with black hole entropy in anti-de Sitter spacetimes.
Sorry for such a long title. When you interrupted me in my office looking for a title, my brain was obviously in overdrive. So what I want to do is I want to set a puzzle for you. Right? This is a quantum mechanical Hamiltonian. I've written it twice. It's a Hamiltonian in terms of matrices, XA. So they're written out here as XA capital A, where I've expanded in a basis of matrices, which are Gell-Mann matrices typically. And the commutator gives rise to structure constants of SUN. And we've got this is just a nice potential, and these are fermions. So it's just a simple quantum mechanical Hamiltonian. A little bit complicated maybe because it's got these large number of degrees of freedom. It's got bosons and fermions. Sorry, I'm going. Now, this is not going to work. Okay. I may use this instead. But there's an additional constraint. The constraint is that you only look at invariance, UN invariance. It's easier to see what UN invariance mean when you spill out all the indices. They are the capital indices XA. So the invariance cannot have any exposed indices. So one's looking at the properties of this Hamiltonian. You will notice as well that it has the potential here has a commutator, so that if two x's, two diagonal matrices commute, so there are flat directions in the space of x's, of degrees of freedom. They're associated with these antisymmetric part of these F tensor here. So it's got flat directions, it's got fermions. If we suppress the fermions, then it's a very regular Hamiltonian. You can think of it in terms of 2 by 2 matrices. These would be just the cross product of two vectors squared and the momentum for them. It has an additional property that it's supersymmetric. But the key for me is that it encodes details about 11-dimensional supergravity. Such a simple Hamiltonian encoding details of 11-dimensional supergravity. Many tests have been done comparing it with scattering of gravitons in asymptotically flat Minkowski space. But one of the most detailed tests of it is that the ground state is related to, there's a conjecture that it is related to a particular solution of 11-dimensional supergravity. This is part of a family of models, and the set of results fall under what is called gauge gravity duality, which is related to ADS CFT, the duality relationship between conformal field theories and gravitational duals in anti-de Sitter space. So that's the setting. This is an additional gauge field that's in supergravity is quite simple. I haven't written down its fermions. It has a gravitational field, it has a tree-form gauge field, and it has some fermions. The fermions do play no role in the background other than that. No, that's okay, Charles. Thanks. I'll stick with this. The fermions play no role in the background other than that they do define, you can probe supersymmetric solutions by using the fermion. The fermion that's natural in this setting is a spin 3/2 gravitino. But this is the setting. And if I will try this one. It goes twice, okay.
There's just a slight delay.
Yes, I just need to get used to it. Hopefully, yes. So this is the solution to the 11-dimensional supergravity. For the model that I showed you, only the gravitational sector plays a role. The tree-form gauge field is not. If I went to a related model, which is called the BMN model, you turn on that tree-form gauge field, and it warps the geometry in a particular way. So this is the metric, very simple one. The tree-form or the H field, it's on an 11-dimensional space-time with a circle. And this is a circle that's warped over the space-time. So it's like a little bit, it's related to Taub knot. It's that type of circle, if people know what that means. So that's the gauge field. And if I, yes, okay. For that Hamiltonian that I described, one can look at the thermodynamics associated with that Hamiltonian. Trace of e to the minus beta h, and I've just written down the invariant states to say that the only states that are permitted in this are the ones that are UN invariant. Now, what is known as well at the level of conjecture and with substantial evidence for it is that there is a gravitational dual, previous one that I showed you, this geometry, you add a black hole to that geometry, and the temperature of the black hole is the Hawking temperature of that black hole. So, yeah.
Sorry,
Yeah.
I was confused about this. When you say you have a black hole, where does it show in the metric? I mean, you think, at least I would assume that you see a black hole and your space-time metric should represent it, or have I not understood this?
You're looking for my next slide, I believe, which I just showed you the metric again to show you that what it is. So this is what the metric looks like, and it has this black hole factor, which is familiar. F is this 1 minus the radius. U is the radius divided by alpha prime. One scales it because you want to look at particular energy sector of it to make a comparison, and it should be when alpha prime is comes from an underlying set of ideas associated with string theory, and one wants to suppress the higher string modes. So the real duality should be at finite n, and the conjecture exists that there is a duality between this particular model and full string theory in related backgrounds when I don't have alpha prime going to infinity. So this is just a rescaling. But what it does is it kills the 1 in this factor here, in my h, no, in the original h. So h is now just scaled with this 1 u to the 1 over 7. So this is what the metric looks like. Very simple solution. The original one is a solution to 11-dimensional supergravity with a black hole background in this periodic time direction. Oops, I forget that. This is frustrating for me. Okay. So you can deduce from this just what the Hawking temperature is from the black hole geometry. It's given by the surface curvature, and you relate it to the parameters of the geometry, and you see that it has a particular scaling. The entropy is the area divided by 4 times Newton's constant. This is the 11-dimensional Newton's constant, and it gives you this characteristic exponent t to the 9 over 2, or that the energy, which would be related to the mass of the black hole, is related to t to the 14 over 5. And this is where that detailed conjecture, you can find the details of it. So that's the thing. So my question is, where is that geometry hiding in the simple matrix model? It's in there somewhere, if we believe the conjecture, so how can we disentangle it? But what I wanted to do first, there just to compare, one of the things one can do with that basic quantum mechanical Hamiltonian is one can compare, see if numerically the model is not solvable, there's no known solution to it, but you can do comparisons using Monte Carlo simulations of the energy, measure the energy as a function of the temperature and see if it agrees. So this is relatively old one now, but this is still the best comparison, and the agreement is rather striking. Some of the 1 over n corrections are known from higher derivative gravity. 1 over n are the quantum corrections to the geometry that one expects from that notion of membranes and propagating in that background and the M-theory set of ideas. But anyway, so the simple question is, where is that geometry hiding? So I just wanted to review, first of all, since it's closely related to ADS, this is just a warped version of ADS that's sitting in 11 dimensions. So I wanted to review where that black hole entropy is, or how the set of ideas associated with ADS black holes. And that's an old paper of Hawking and Page, so I'm just going to more or less copy it, generalize it to d dimensions. Oops. This delay is frustrating me. So I forget whether I've pressed the right one or not. So, yeah, okay.
There's 2 black holes in this case, aren't there?
No, it's just one. There's just one black hole.
I thought there was one negative specific heat. Is that?
It's the one black hole, but you vary the mass of it. I will show you that. I want to focus in on that in detail. So this is the anti-de Sitter space-time solution. F of R. I've written it down. There's a scale associated with de Sitter space, anti-de Sitter space, which is given by the cosmological constant. And this is just a solution to Einstein equations with a negative cosmological constant, with a black hole sitting in it. So the black hole mass is m, and it has a Schwarzschild radius, or the horizon is sitting at RH, and RH is where this function has a 0. It is useful to parameterize everything in terms of R plus. In terms of this one. So the entropy, which is the area divided by 4 pi g, it is given by just some geometric factors times this r to the d minus 2, and the mass is given by some other geometrical factors, and it's parameterized in terms of r plus. And as you can see, that it is, both of them are monotonic functions of r plus. So that's the setting. The Hawking temperature, did I go 2 or 1? They flash at different times. Okay. The Hawking temperature is, in this case, it's a d-dependent parameter. The energy is given by this, right? One can go to dimensionless units. Everything is determined in terms of the scale associated with the cosmological constant, the scale of curvature of anti-de Sitter space, R plus over L. And if I do that, one can plot the temperature energy curve. Right? The temperature energy curve for very small energies when we were down, this is what the temperature energy curve looks like. It's parametrically plotted in terms of R plus. And this is what Charles was mentioning. Down here, you see that as the energy increases, the temperature goes down. As the black hole gets smaller, it gets hotter, right? The temperature goes up. So, whereas if I go to scales larger than some fraction of the scale associated with this, then you get into what are called large black holes in anti-de Sitter space, and these ones have positive specific heat. Right? Positive, they're naturally, this is negative specific heat, Schwarzschild-like, so we're Schwarzschild-like down here, we're anti-de Sitter-like up here, and there's an instability that this negative one here, well, it should be unstable in that it radiates. Anti-de Sitter space behaves like a box, so it fills up the space with radiation from the Hawking radiation, and eventually the black hole disappears. The more stable situation is the radiation. So it's just like boiling water, steam. We have steam up here, water here, bubbles of small black holes in this region here. And there's a Hawking-Page phase transition. The conjecture is that this Hawking-Page phase transition is related to the confining, deconfining phase transition in gauge theories. So that's the setting. If I suppress the fermions in that original Hamiltonian, one can see that it has exactly a Hawking-Page type phase transition. It has a confining, deconfining phase transition. And it is closely related to a dimensional reduction of Yang-Mills. So I want to go back to the gauge theory. And so the quest is, let's see what we can figure out about the quantum mechanical model. How can we find evidence for the black hole states? Where are they hiding? Right? So just a little bit more detail on what that quantum mechanical model is. I wrote it out as a set of matrices. There are D of them. There were 9 of them in the original model, in the BFSS model, but we can take it to be D of them. They transform under UN, and this is because a trace is invariant. A product of traces of matrices is invariant under this gauge transformation. Right? The invariant states then are ones where they're built from traces and powers of traces, products of traces, etc., of those matrices. And we are summing over those, and you're going to get a partition function. And if I look at the count, this is a counting problem in the end. If I want to know how many of those states are, I've changed the Hamiltonian here to be the number operator. So I'm just going to take the number operator, and I'm defining x to be e to the minus beta. So k, if I'm in an eigenvalue of n, I get k here. So k is telling me how many x's there are, and I can count the number of states that have a given number of x's in them. That's
so the e to the minus beta n, so the n should have a hat on it.
That's one convention. I wrote it as bold. But
you had h equal to n hat.
Do I have n? Oh, yeah, it should have a hat. I forgot. There's a typo. I should have kept it consistent. Sorry, I didn't spot that I had. Yeah, there's only this one. This in and this in are meant to be the same. Sorry, I didn't. And this in was supposed to be the size of the matrix. I have too many n's. Right. So my Hamiltonian is that is so. This then is just counting them. The reason for just counting states is because if you vary the Hamiltonian, the space of states is still the same. you're going to get mixing between different states, but qualitatively you expect very similar physics. So that's the idea. And we want to just track what's happening here. So we can count those ones. This is a problem in invariant theory, count the number of states of those things. And just to give you an example of how it works, if we just took a single matrix with the number operator for that matrix, which is the trace of A dagger A for that matrix of creation operators, then the partition function is this classic function here, product from n equals 1 up to capital N of 1 over 1 minus x to the n. And it tells me that if I expand it out, the number of states at any given level that are invariant is built from taking trace of x, powers of trace of x, up to n. You're not allowed powers greater than n. And you divide those ones into partition of n, and you say, well, how many traces of x squared, traces of x to the n? You get a partition of the integer capital N, of the integer k into n parts. So k is an integer, you divide it up into n parts. So that's classic partition function, and that counts the partition function that comes from just one matrix. One matrix is not very interesting. Well, maybe it is if you're interested in such things, but it has much less rich structure than if I consider many matrices. So the invariance associated with D matrices, sorry, I should say that for one matrix, Cayley-Hamilton tells me that that the power higher than k of the matrix is related to lower powers because it only has n eigenvalues. So you can re-express any higher power. That's why there was a cutoff in the product there. So if I take the invariants, they're built up from traces, products of different traces, and this is the counting that I will get from them. This is related to various other things which I don't want to go into at this point. The strong thing that one expects to be able to connect between the low energy physics and the high energy physics is the symmetry. We want to connect the low energy physics associated with this Hamiltonian with a strong coupling physics associated, which was going to be associated with large n and relatively large number of states associated with the system. We want to connect the symmetries. Well, if we want to connect it with a black hole in the higher dimensional state, the natural thing to do is to try and look for invariants that are similar to the black hole invariant states. So the black hole in equilibrium in anti-de Sitter space has spherical symmetry. The horizon is spherical. The entire solution was written in terms of one variable r. That was the one that parameterized everything. So the metric has in fact orthogonal symmetry as opposed to OD, because you can change the orientation and it will look the same. So, just as I said, the states are associated with creation operators. If we can think of them, somebody was asking? Okay. We can think of them as creation operators that are related to those states, related to those matrices. If we think of it in terms of a Schrodinger type picture, we would think of wave functions with some exponential and products of these things like products of the invariants. And if I look at just k equals 2, and I want to now concentrate on not just UN invariants, I want to concentrate on SOD invariants or OD invariants. So what they're telling you is contract all of these ones, these i's and j's, with different deltas. All the different ways are related to permutations of the indices, and all of those ones give you the possible different contractions that will give you the UN invariance. If I want to connect the SOD indices, well, I can connect them with either deltas or epsilons. If I kill the epsilon contractions, then I'm dealing with OD rather than SOD invariance. And the different contraction ones are associated with different invariants. So here for any n, there at k equals 2, I'm showing you there are only 2 invariants for SOD UN invariants. These are joint invariants now of that system. One can relate the counting problem, and this works out rather neatly if one takes it from a path integral point of view, that one can find this path integral, which is, I'm now taking it to be the OD invariant one. It amounts to an inverse of the determinant averaged over the groups. And this is what's called the Mullian-Weil formula. This one, I think I wrote the same thing twice by accident. There's supposed to be, there's a sum over 2 terms here for OD. Yeah, okay. And mu of SOD is the Haar measure on the orthogonal group, and mu of UN is the Haar measure on the unitary groups, and X is that. So this gives you a counting problem. One can handle it for small values. You can handle it by contour integration. For larger values, there are other tricks that one can use. But I don't want to go into the details of that. What I'm interested in is the asymptotics of the counting. The asymptotics of the counting changes when I look at OD invariance. If I look at just the UN invariance, what the low energy counting, it just grows, the number of states grows as d to the k, which is exponential growth, which it can only be valid for small energies. This should break down because the growth of energies, of number of states exponentially with energy is characteristic of what's called the Hagedorn transition. And those things, anyway. So this is estimated in what's called the stable region when the number of, when the matrix size is larger than k. In other words, Cayley-Hamilton is not playing any role. When k, this number of states is larger, there are relations between the invariants and the counting changes. So this is the asymptotics in that large k, large n, but k being less than n. It grows this way, but with a new factor of 1 over k to the d times d minus 1 over 4. If I count in it at higher energies, from different methods one can estimate the number of states at high energies, which is above the transition. One gets a slightly different formula that the number of states drops off exponentially. So that's a counting problem. It means we've access now to the microcanonical ensemble for this quantum system. It has non-trivial behavior. This is characteristic of some transition where at some very large but still finite n, it transitions from this exponential growth to cut-off exponential growth. This is no longer growing exponentially because we've got an e to the minus term here.
K is an integer, isn't it?
K is an integer.
So you can't always have k equal to n squared over 4.
No, you can't. I don't need it to be equal, but you can get arbitrarily close for large enough n and k. But now one can look at what the microcanonical ensemble tells you by just computing the microcanonical temperature, and you know that the entropy is going to be related to the log of the number of states. So microcanonical ensemble, numerically one can take this as a finite difference. This is just finite difference of the logs. which is giving me a ratio, and this is symmetric difference. This is an approximation to the derivative. So by going through details of that counting and looking at it without the gauge invariance, without the rotational invariance, you get a phase diagram that looks like this. So if I look at it by imposing that rotational invariance, well, you get something that looks much more characteristic of the ADS structure. You have negative specific heat transitioning to positive specific heat. And in detail, what you have is you have put a constraint that you are only looking at OD invariant states in a system which naturally has many more states. So this is a subsystem of this larger system. It's unstable down here and stable up here. So you can see that the microscopic nature of the transition looks much more similar to the ADS setting. And the conjecture is that these SOD invariant states should be the natural candidates for the microstates that are giving rise to the black holes in that. That's where one should be starting for them. So the key observation is that at low energy with negative specific heat, high energy you get transition to positive specific heat. One can track the transition that it occurs approximately, it scales as n squared over 4. There's some nice mathematics going with that, and these are the key results, and I'm probably out of time. Okay? So, thank you.
Right, so I think if anyone wants to ask Denjoe any questions, you can do so at the reception.
Sure.
We'll be there?
That's fine.
Yes. Otherwise, thank you all for coming. There's going to be a reception downstairs, but before we go, first of all, take a folder. And yeah, I'm just going to hand over to Rick to close up.
Okay. Well, thank you so much, Josh. Okay. Thanks everyone for coming, and well, first of all, let's all thank Josh for organizing this. So Josh, thank you. Also, let me thank Yasaman for helping fund this whole thing, and Dias overall for hosting everything. I think that this was a very nice addition to the series of conferences, this RQI Circuit. It's very nice to see different perspectives of quantum gravity and be able to put together the different kinds of research being done here in Dias. So it was a pleasure to watch this, and hopefully whoever is watching this will also enjoy the pleasure that I had. So just final remark is just that next week we'll be in New York. So we heard a lot about von Neumann algebras here, of type 2, type 3, and all of these things. So probably next week, if you're interested in these things, there will be many more talks about these topics. Feel free to tune in through YouTube, or if you guys want to travel to York, contact the organizers. You can actually be there in person too. So again, thank you so much, and until next week for whoever wants to watch it.